Hello, and welcome to the Network Technology and Security course. In this course, we'll start with a look at the OSI model. That's the Open Systems Interconnection Model from the International Organization for Standardization. Then we're going to look at a series of protocols that are part of what we would call the TCP/IP suite of protocols. And we're going to take an introductory look at several of these core protocols that are used with our standard networks that we use on our corporate networking environment as well as on the internet. Following that, we're going to look at transmission media and transmission technologies. We're going to be looking at how do the bits and packets and frames commute from one node on a corporate network through the routed environment to the destination node on that network. Next, we're going to look at the networking infrastructure. These are many of the core pieces that are essential to establish a functioning IT system. The next section is going to look at more the size and nature of these different sized networking environments. Everything from a very small personal area network, which is limited to about a 10-meter radius, all the way up to the wide area network that would span the globe. Following that, we're going to look at a rapidly evolving new area of networking, and this is wireless networking. So we're going to take a close look at how do wireless networks operate and how would we secure those wireless networks, because they are inherently insecure, non-secure, and as a result, we need special attention to securing them properly. And in the last section, we're going to look at different types of attacks that have been implemented on our corporate network. The more we understand the attacker's perspective and the nature of these attacks, the better prepared we are to defend our networks against those attacks. This lesson is going to cover the OSI model, the Open Systems Interconnection Model. This model was developed by the International Organization for Standardization. This is an organization that establishes best practices and recommendations that are adopted globally. And in this particular case, the model is designed to establish a single and common network stack for every application on a computer system so that each application can share this one path out to the network. The OSI model is divided into 7 layers to allow for a highly specialized grouping and focus on the different functions that occur at these 7 layers, as the information that a user of a computer is trying to send across the network, as this information is organized and prepared so that it can commute across essentially any sort of network that we might utilize in a corporate environment or in the home environment. So again, the goal of this model is to establish a single and common network stack within the network operating system so that all applications can use that network. These 7 layers are numbered from the bottom layer to the top layer. Bottom layer being number 1, top layer being number 7, and they follow this order: physical, data link, network, transport, session, presentation, and application layer. As you see to the right-hand side of this network stack shown on the slide, the top 3 layers, the information remains in a data stream. And then at layer 4 of the OSI model, the transport layer, we take that data stream and we break it up into segments. And that's where we begin to establish the headers for each segment. So at layer 4, we would have the payload, which is the actual part of the data file that the user is trying to send over the network. So we break that up into small chunks called segments, and then we add in front of that payload or segment the information in the headers for the layer 7, 6, 5, and 4 headers. At layer 3 of the OSI model, we add yet another header, and this now becomes a packet or datagram at the network layer. As this information flows down through the stack, we reach layer 2, where we complete the frame, where all binary bits are lined up in the proper order, complete with all layer 2 through 7 header information and a CRC trailer. And this is also where the computer or the node senses the network media and determines whether or not it's safe to begin transmission of this information out onto the network media. Now at layer 1, this is where the information is communicated as binary bits from the network interface card out into the actual network media itself. The order of these layers is important for you to understand, to memorize, especially if you're taking any sort of certifications. This is one of those classic models that almost every IT certification gets involved with to some extent. So as we move from the bottom to the top, we've built this mnemonic, this tool to help you memorize these layers. Please do not throw sausage pizza away. Represents the P for physical, the D for data link, N for network, T for transport, S for session, P for presentation, and A for application. Here we see a user on the left-hand side who is using a computer and applications, and in the use of one of his applications, he desires to send a file from his computer to some other computer or node across the corporate network. As we can see, the information that the user on the left is trying to communicate to the user on the right has to pass down through this network stack in his computer. This is actually part of the network operating system. And at each layer of the OSI model, we process the information that is being transmitted from sender to receiver, from source to destination. And we process it in a different manner depending on the nature of the network and whether or not we're encrypting and compressing and who that remote node is, the capability of that remote node. So a whole lot of information has to be aggregated as we begin to prepare this information for its transmission across the network media to the recipient or destination. So the information flows down through the network stack, down through the OSI model, and when we get it all completely prepared and ready to go out onto the network media, we are transmitting binary ones and zeros using a technique called modulation and encoding, and we transmit it over to the destination. At the recipient side, the right-hand side, we then have to undo every change we made to the information that we've sent across the network. We have to undo it so that we can put that information back to its original state, back in its original form, so that the recipient on the right can actually see the same exact data that the sender on the left actually and originally sent. Layer 7 of the OSI model is the application layer. The application layer is considered to be the most intelligent layer and also the most abstract layer. And we say abstract relative to the physical layer, so this is most abstract from physical reality. In other words, think of the application layer as the receiving hands of all data that the applications up above are sending out to the network. Now, applications don't live at the application layer. This is simply the receiving hands for applications up above to get towards the network stack. We should also take a look at the protocols that operate here at layer 7. One of them I want to point out is DNS, the domain name system, because this function of name resolution happens here when we first identify who it is, what node it is that we're going to transmit this data to on the remote endpoint. So again, layer 7, the most abstract, the most intelligent, and the receiving hands for all the data as it moves towards the network stack. The next layer down is the presentation layer. Now think of this layer being the layer that converts the information that's coming down from the applications into a format that is compatible with the network that we're going to be sending this data across. So here we're going to do things like encryption and compression, but we must convert this data from whatever format it's in into a format that is suitable for the network. Once again, if you would notice some of the protocols that operate here at layer 6 of the OSI model, the presentation layer. Now we're going to take a break here as we march through the OSI model, and we'll pick up where we left off on the next video. Now the session layer is where the source node, that's the sending computer, reaches out and actually contacts the destination computer and begins to negotiate session-related details, including the setup of the session, maintenance of the session, recovery, synchronization, and eventually the teardown of the session as we complete the transmission. Basically, we negotiate who speaks, when do they speak, and for how long do they speak. If you would, please notice several of the protocols that operate here at layer 5 of the OSI model. The more you recognize and remember these protocols, the better you will understand where they fit into the network engineering and network administration of your IT environment. Moving on, layer 4 is the next layer of the OSI model, the transport layer. Now, this is where we actually make some real changes to the information that we're actually sending out over the network connection. Here at the network layer, we take that large data stream that was the file. Now remember, computers store their data in these long strings of binary bits. We call that long string of contiguous binary bits that make up a file. We call that a data stream. So at layers 7, 6, and 5, it's all been this long contiguous data stream. Here, finally, at layer 4 of the OSI model, the transport layer is where we chop up that long data stream because we can't put that much data on the network for that long a period of time. So we're going to break it up into tiny little chunks called segments. And we're going to build approximately, for a standard Ethernet network, about a 1 kilobyte payload. And then we're going to add in front of that payload, that is the data that we're actually trying to send to the destination, we're going to prepend layers 7, 6, 5, and 4 header information that will tell the destination what changes we've made to this payload, so that at the destination, when they're beginning to process the information they've received, they can undo or reverse the procedures that we've performed to put this payload back into its original format, into its original data stream and file format that it was before we ever started transmitting it out over the network. So we have to make some changes to the data as we transmit it, but then we have to undo those changes on the recipient side so the recipient can actually receive the file as it was originally before we started sending it across the network. Now, there are two primary protocols that operate at this layer of the OSI model. That would be TCP and UDP. And these are some of your primary networking protocols. If you recall, our primary protocol that we use on the internet is TCP and IP. Well, boom, right here is TCP at layer 4 of the OSI model. Now, in addition to choosing whether or not we're using TCP or UDP, we also would identify the source and destination port numbers that would be utilized for this particular data transmission. We'll be reviewing what TCP and UDP, what these differences are, and we'll also be reviewing some of the details about these source and destination port numbers in a later section in this series of lessons. As we move forward through the OSI model, we next look at the network layer, layer 3. Now here is where IP, the Internet Protocol, operates. Again, that's one of the core protocols that is used on this global network we call the Internet. So TCP from layer 4 and IP are some of our primary protocols used for networks. So we have to identify the source and destination IP addresses. Source would be the sending computer. Destination is the target computer, the recipient that we're trying to send this information to. And so we have to have this information built into the layer 3 header that we add to the front of this now packet or datagram here at layer 3. So layer 3 is all about addressing, and today, more specifically, it's almost exclusively IP addressing, the Internet Protocol addressing. And then routing functions occur here at layer 3 because we are routing based on these IP addresses. Again, please notice some of the protocols that operate here at layer 3 of the OSI model. We currently are operating on IP version 4, and we are migrating towards IP version 6. Some devices that operate here at layer 3 of the OSI model are the router, because the routing function is based on IP, and the IP information, the IP protocol, lives here at layer 3 of the OSI model. So the router lives here at layer 3 of the OSI model, and because the router was the very first firewall, the packet filtering firewall also operates here at layer 3 of the OSI model. At layer 2, we now have the data link layer. And the data link layer has a whole lot of activity that occurs here, so it has been broken up into the higher logical link control, the upper layer of layer 2, and it has a lower sublayer called media access control. So the data link layer is generally thought of as being divided into two sublayers, logical link control and media access control. We say media access control operates here at layer 2 because this is where a sending node senses the media and determines when it is proper for this node to access the media by transmitting out to that media. So the merging of your data onto this shared network media is determined here at layer 2 in the data link layer. In addition, we add source and destination MAC address, media access control addresses. So the source address would be an address that is identified by your network interface card, and the destination MAC address isn't necessarily the recipient of this information, but it is the next hop in the path to the destination computer, the actual recipient. So we'll add the source and destination MAC addresses to the layer 2 header that we add to the front of this now frame, and then we run a cyclic redundancy check, which is a very crude 32-bit hash function, and we generate the hash value for the very beginning of the layer 2 header all the way to the end of the payload, and we use this as an error detection technique to identify if any corruption has occurred to this now frame. We now have completed the frame, and this is the complete set of binary bits, ones and zeros, that we will use to transmit across the network. As soon as now media access control methods kick in, the node identifies when the media is free and it might be safe for him to begin transmitting his data out onto the media. And at layer 1, the next layer down, is where we would actually begin to pump those ones and zeros out onto the media. But the determination for when that happens occurs here at layer 2. Again, please look at the protocols that operate here at layer 2. A primary protocol I want to point out is the Address Resolution Protocol, ARP. This is how we identify the destination MAC address. And also we have the switch, the bridge, and the bridging function of wireless access points are devices that operate here at layer 2 of the OSI model. Now we mentioned media access control. That's how we merge our data onto the wire. And we also mentioned a media access control address. Again, this is a 48 binary bit address that is hard-coded onto your network interface card, the NIC. As we see, the MAC address is typically written in pairs of hexadecimal characters. The first 6 of these hexadecimal characters uniquely identify the vendor of the network interface card. The last 6 characters represent a unique address for this particular network interface card from that vendor. Now finally, at the physical layer of the OSI model, this is where binary bits occur. The physical layer is the dumbest of all, but the most real, the most tangible layer of all. Why? Because these are physical components. Again, this layer does no filtering, no intelligent conversions or anything other than modulation and encoding of binary bits onto the media. So that's all that happens here at the physical layer. Sending node puts binary bits down onto the media, and the receiving node pulls the binary bits back off the media and hands them upstairs for further processing. The primary protocols that operate here are more in the wireless realm. These protocols that are listed here deal with wireless networking, which we're going to review in a later section of this particular course. And some devices that operate here at layer 1 of the OSI model are the hub, the network interface card, the media itself, that's like an Ethernet cable, and we have repeaters, amplifiers, the connectors, and also on wireless access points, the actual radios and antenna that generate the radio frequency signal that is used to modulate and encode the binary data bits into the airwaves. In this lesson, we're going to take a look at the TCP/IP suite of protocols. At layer 4 of the OSI model, we find 2 of our primary protocols used on all corporate networks and across the internet as well. And they are the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP. Now, these 2 protocols are competing protocols. A segment will only use either TCP or UDP. And really, it's a matter of how certain is it that we have to get this information to the destination. If it's really important that you get this packet, this segment, this payload of data to the recipient, then you'll pay a higher price and use a more certain delivery mechanism, and that would be TCP. If we're doing that recipient kind of a favor and it really doesn't hurt us much if he doesn't get this information, then we might use a cheaper and faster protocol called UDP because it is fast and cheap and has very little overhead. Now, typically it's the application developer who wrote the application that created the data. He's the guy who knows what this data is and how important it is that we get 100% of this data over to the destination anytime we need to use the network relative to this application. So the guy who wrote the program makes a determination whether at layer 4 of the OSI model, the transport layer, we will initiate the TCP protocol, high cost, slower, but guaranteed delivery, because TCP is connection oriented. Before the sender starts sending any TCP segments, the sender will reach out to the destination and establish a session, a connection, by using a three-way handshake. The three-way handshake is 3 frames from source to destination, is sent a SYN or synchronized frame. The destination sends back a synchronized acknowledged frame, and then the source sends to the destination an acknowledged frame. This three-way handshake, these 3 frames establish the connection or the TCP session between sender and recipient. So that's the connection-oriented part, and that is 100% overhead. There's no actual data that commuted the network during that transmission. Now, the guaranteed delivery comes by the positive acknowledgement that the recipient must send for every segment he receives. So when the recipient understands they've established a TCP session with the sender, every segment that arrives, the recipient will process it up the stack to layer 4, verify that the payload looks like it's intact, and then at that point send an acknowledgement frame back to the sender for this segment that was just received successfully. This way the sender knows that it got delivered. Now, if a segment goes without an acknowledgement being returned to the sender assumes that the segment got lost and will simply retransmit that segment back to the recipient. So this is the guaranteed delivery of TCP. Now, UDP, as we said, is quite different from TCP. It has no overhead or very low overhead because there is no connection, no session established. There's no three-way handshake. So there's none of that overhead associated with UDP. When the UDP segment is ready for transmission, the sender simply sends it out. And that's the end of the story because there also is no acknowledgement expected or required from the recipient. So the sender simply puts the data on the network media and then assumes that it got delivered and doesn't actually know or care whether it really got delivered. So it is considered to be connectionless because there's no session established. It is also considered to be best effort delivery because there is no acknowledgement required for any of these segments that are delivered with UDP. Now, another thing that happens here at layer 4 of the OSI model, the transport layer, is the identification of the source and destination port numbers. These port numbers range from 0 to 65,535. There's a series of these that are referred to as server-side ports, also called well-known ports. And then there's a series of these port numbers that are referred to as client-side ports that come out of what we call the ephemeral port range. Now, ephemeral implies that these are temporary use. So here's how this works. A server on the network has a listener, an application that is listening for inbound requests for the particular service. That listener is bound to a port number, so that when a request comes in to a specific port number, the server understands what service is being requested. The server hands that request up to the appropriate server-side application. If you look down at the bottom of this screen, you'll see a collection of the server-side port numbers that come out of the well-known ports. These well-known ports range from 0 to 1023 and are typically bound to server-side applications, services that run on your network that a client may request. So if a client is opening his browser and he wants to browse a web page, he'll send the request to server-side port 80. That would be the destination port 80. And that way, when the segment is received by the server, it looks at the port number at layer 4 header and says, oh, hand this request up to the web server. Now, the client must also receive that information back and hand it to the proper application running on the client computer. So the client also picks up port number out of this ephemeral port range, also called the client-side ports, ranging from 49,152 through 65,535. He simply makes up a number out of that range, let's say 58,000, and uses that as his source port number when he sends out his request. Now, when the web server sends a response back, he sends it to destination port 58,000, and the client now knows to link this payload to the browser, and he hands that data back up to the browser so that the web browser can properly process this data. So here we have in the layer 4 header, TCP and UDP, we have source and destination port numbers that are also identified in this layer 4 header. Now, here is a list of protocols, network services, if you will, and their associated port numbers. As you can see, most of these port numbers range in that server-side port number range from 0 to 1023. However, we kind of overran our expectations on the number of server-side services that might eventually be needed on a network. So you see some of these server-side port numbers went outside of that well-known port number range, 0 to 1023. With this, we're going to take a break and we'll pick up with our TCP/IP suite of protocols in the very next lesson. In this lesson, we're going to be looking at several others of the TCP/IP protocol suite. Let's start with the Internet Protocol version 4. This is the layer 3 network layer protocol used by almost every corporate network and used by the Internet. So this is one of our primary core protocols used on all of our networks. Now, the IPv4 address is a 32-bit binary address. In other words, it uses a string of 32 ones and zeros to identify a typically an unambiguous destination. In other words, when you want to send a file to a file server, you want it to go to a very specific file server, so this address must be unique and unambiguous to identify that file server uniquely. So we have a 32-bit binary string, and we see that about the second line down here on the slide. But off to the left of that, what we see is the dotted decimal notation for that same IP address. So the binary is to the right, the dotted decimal, something us humans can understand, something that might look more to us like an IP address, is off to the left. Below that, what we see is what we call the subnet mask. Now, if you'll notice, in binary, the subnet mask is a string of ones followed by a string of zeros. And in this case, this subnet mask is what we call a /24 mask insider notation. That's classless interdomain routing notation. And what that /24 designates is that the first 24 binary bits in this subnet mask are ones. And if the mask has to be 32 bits, that says that there are 8 remaining binary bits that have to be 0. Because we only have those two choices. It's either turned on as a 1 or it's turned off as a 0. Now, what this mask identifies to the routing system, that also is a layer 3 network function, is which part of this address, 192.168.10.83, represents the network that the computer node, in this case a destination node, might be on. And the portion that is masked by zeros identifies which host or node on that network the destination is. So it's kind of like a boulevard and the house number. The boulevard is the subnet ID, and the house number is the host ID. The boulevard is identified by that string of ones in the subnet mask, and the house number is identified by the string of zeros in that subnet mask. An IP address is incomplete without both the IP address and its subnet mask. We don't understand anything about that node without knowing its subnet mask. So anytime you identify a node, you statically assign an IP address to a node, you must provide at least these two pieces of information. Now, typically, when you're configuring a node on an IP network, you will also need two other pieces to actually make it functional. Those first two, IP address and subnet mask, are essential, and the node simply will not operate without those two pieces. If you give it those two pieces, it'll operate on the network, but only on its local subnet. If you really want to operate on the internet or a larger corporate network, then you'll also need a default gateway, which is the IP address of the router that this node will attach to. So your default gateway is a router's IP address that is your path to all other networks, and that's your default gateway. And then the next thing almost all IP clients are going to require is a IP address for a DNS server. And because it's so important to have this DNS service available, very often you will identify not one but two DNS servers. One is the primary, the preferred, and then the second one is an alternate, just in case that preferred server is unavailable. So what is DNS? DNS provides us name resolution to the IP address for that computer's name. Humans do not understand IP addresses nearly as well as they understand friendly names. So if I'm trying to save a file to my file server 1, I have no idea intuitively what the IP address is for file server 1. But I do know his name is file server 1. So I type in, I want to send this to file server 1. Well, DNS is the service that converts that friendly name that is intuitive to us humans, file server 1, into the IP address for file server 1. So it's a database of these mappings of friendly name to the IP address. And almost all nodes will need at least one and ideally two IP addresses in order to function properly on a larger network. Here we see the family of IPv4 IP address classes. We have a class A, B, C, D, and E. Now, on corporate networks and on the internet, these nodes are all identified by IP addresses out of classes A, B, or C. These ranges, class A is 1 to 126, B is 128 to 191, and class C is 192 to 223 in the first octet of the IP address. These ranges are the ranges of IP addresses that you can assign to nodes on networks. Now, Class D is reserved for a special protocol called Multicast, or Internet Group Management Protocol, IGMP. And in this case, a multicast protocol will send one data stream out from a source computer, and it will assign Class D IP addresses to any number of nodes, client computers, that opt in for this particular transmission. So suppose we have a meeting that I've recorded and I want to send it out to 10,000 clients. I don't want to build a TCP session to every one of these clients because of all the overhead associated with it. So what I'm going to do is I'm going to set up a multicast transmission, and I'm going to identify to these 10,000 clients, we're also going to bind a second Class D IP address to your network interface card. And we're going to pick a number, let's say 226.0.0.19. And I'm going to give that same IP address to all 10,000 recipients that I want to receive this video. And then I'm going to send my video stream out to that same IP address. And the routing system will duplicate and distribute these frames to those 10,000 IP addresses that are all that same number that I identified. So that's the nature of multicast. So therefore, typically it's an application that sends those IP addresses or assigns those IP addresses to nodes. Finally, that Class E IP address is experimental, and generally we can't assign anything out of that either. So the Class D and E aren't IP addresses we generally would assign to nodes, statically or by DHCP, but Class D is generally assigned by application, and Class E is generally not assigned at all. Down below, we see a series of IP address ranges that are defined for private networks and generally are not usable. The first three are not usable on the public internet. So all the routers on the public internet are configured to discard or drop any packets with a source or destination in any of these three ranges, the 10 dot, the 172.16 dot, and the 192.168 dot. These are private address spaces to be used behind corporate firewalls. Automatic private IP addressing is an address that gets automatically generated if your node, your client node, does not have an IP address available. It will make one up out of this range. Again, these are not routable. Now, the first three are routable on private networks. This fourth one, 169.254.0.0, is not routable at all because there isn't a default gateway option with automatic private IP addressing. Therefore, we can't find our way through a router. And finally, the 127 IP address range is defined as diagnostic, and this is where we get our loopback address for testing purposes, 127.0.0.1. That's our loopback address. So these are families of IP addresses that are probably some of the more important ranges you should be aware of. In this lesson, we're looking at ways to identify what your current and local IP configuration is. On a Windows computer, you can type the command at a DOS prompt, ipconfig/all, and that will show you all of the details that are available for this particular network interface and the IP configuration that is associated with that network interface card. Now, on a Linux computer, the command is typically ifconfig-a, and you'll get a similar type of collection of information presented back. So in a Windows world, you get yourself to a command prompt, you type in ipconfig/all, and we can identify the host name of the computer. In this case, it's Momotambo. The domain affiliation is boboville.com. We then, looking down below, we see the Ethernet adapter, local area connection. We see the nature of the network interface card. That's the manufacturer and the model number. Below that, we see something called the physical address. Now, this is also referred to as the MAC address, the Media Access Control address, that is hard-coded onto this network interface card. So the first 6 characters of that MAC address represent the manufacturer, and the last 6 characters of that MAC address are a unique value for this network interface card from that manufacturer, defined by the first 6 characters. You notice these are 12 characters in hexadecimal. It's a 48 binary bit string. We scroll down a little bit and we see the link local IP version 6 address. That's just for future reference. We're going to look at IPv6 in another lesson. We'll move down past that. Then we see the IP version 4 address. And in this case, it's 192.168.222.100. And its subnet mask is 255.255.255.0. That equates to a /24 mask. In addition, we see the default gateway of 192.168.222.254. And finally, down below, like the last 2 or 3 lines, we see the DNS servers, and in this case, 2 are listed, 192.168.222.254, and also a second one at 2.2.2.2. That's as if your first DNS server for name resolution at 222.254, if that server is unavailable for any reasons, then go talk to the other DNS server at this 2.2.2.2. Now, that IP address is out on the public internet. First, 192.168.222.2.54 comes out of the private IP address space. That would be a DNS server on the corporate network. The second one is a DNS server out on the public internet. Moving forward, we're going to take a look at IP version 6, another layer 3 network layer protocol. Now, because we started running out of IP version 4 addresses, they have started generating and implementing IP version 6 addressing. IPv6 uses 128 binary bits, in contrast to the 32 binary bits used by IP version 4. So IPv6 is a much longer IP address, and therefore we have many more addresses available. that will allow us to continue to add servers and other systems onto the public internet. Now, IP version 6, because it's the newer version and it has a great deal more configuration ability because of its greater length, we can add extra services into IP version 6. And one of them is called quality of service, which allows us to prioritize packets. Typically, these would be time-sensitive packets like voice and video. We can say, because this is time-sensitive, let him go to the front of the line and let him zip through the network faster than other lower priority packets. So quality of service is generally for time-sensitive packets on a network, and the infrastructure has to have the ability to recognize QoS, but then if it does, knows how to prioritize these and let them go at the head of the line first. IPv6 also has encryption built into it. That was a weakness that IP version 4 did not. We had to generate a brand new protocol called IPsec, Internet Protocol Security, that is different from IP in that added encryption to the IP packets. Now, back to IP version 6. IPv6 address, as you can see here in this example, starts with FE80. And then there's a whole series of zeros and et cetera, et cetera. So what we see is using something called hexadecimal characters. Hexadecimal is a numbering system that has 16 different characters. So I can count from 0 to 16 without reusing any of the characters. What we see is each section in an IPv6 address has 4 of these hexadecimal characters, and each character represents 4 binary bits. So I get 16 binary bits per section. That's a very long IP address, and I'd hate to have to type that in more than once. However, what we can do with IPv6 is we can omit this long chunk of consecutive zeros. And we simply omit these zeros, and what we notice is a pair of colons side by side. So in this case, we've left out those 12 zeros, but because we know that this address has to be a fixed length, we look for the double colon and we simply insert an appropriate amount of zeros to make this the proper length. So we can omit the zeros to simplify the writing of an IPv6 address. Further, in each of these sections, we can omit the leading zeros. So as we see, this one section has 007E. Well, if we look down towards the bottom, we see that we can actually even throw away those leading zeros, and that section simply has the 7E. Now, the end user and, of course, the routing system and the nodes all must understand and actually automatically accommodate this by filling in any missing characters with zeros. So again, we can do these two things to shorten the length of the written IPv6 address. However, the processing automatically adds all those binary zeros back in appropriately. So this is your IP version 6 IP addressing. Now, these addresses are broken up into different ranges, similar to the way IPv4 is broken up into certain ranges. And we have a public IP addressing called global unicast addresses that start with a prefix of 2000. We have unique local addresses. This is equivalent to IPv4 private addressing, and they start with FC00. We have something akin to the automatic private IP addressing in IPv4 called link local IP addresses. Now, these are automatically generated by each node at boot up, and they start with a prefix of FE80. Multicast addresses begin with a prefix of FF00. We have unspecified loopback and default route addresses as well. Now, because most computers today run both a TCP IP4 stack and an IPv6 stack simultaneously, there are times where you'll be transmitting an IPv6, but you bump into an IPv4 only network. In this case, we have to bury our IPv6 packet into an IPv4 packet, and that's called tunneling. If I'm transmitting an IPv4 and I bump into an IPv6 only network, then I have to do something called translation, and I translate that IPv4 address into an IPv6 address. So these are some compatibility or interoperability services that are being utilized as we make the transition from IPv4 to IP version 6. We're picking up here in the TCP/IP suite of protocols. On this slide, we're taking a review of the IPv4 address space so that we can look at the difference between public address space and private address space. As you see on the slide, we have classes A, B, and C for IPv4 addressing. These addresses would be assignable to nodes on a corporate network or on the public internet. Any IP network need to place nodes on. Down below in the blue, we see ranges that are private address space. And if you notice, we have a private address space starting with 10 dot that comes out of the class A. We have a private address space 172.16 that comes out of the class B network range. And we have a 192.168 that comes out of the class C network range. So out of the class A range, everything but this 10 dot network range is public because the 10 dot is private. Out of the class B, everything except the 192.168 address range is public because 172.16 is the private address space. And finally, out of the class D, everything except 192.168 address space is public. 192.168 is the private space out of that range. So the private address ranges are usable only behind corporate firewalls on private networks. And everything else is usable on the public internet. The routers on the internet are programmed or configured so that they will discard any private addresses in the source or destination fields. So these addresses are, while they're routable, they are discarded on the public internet because they come out of the private address space. Now, the public address space is allocated by the regional internet registries. So there are 5 different regional internet registries that are responsible for the allocation, the assignment of the public IP addresses. So these 5 regional internet registries will allocate the public address spaces relative to their geographic locations. Moving forward, we're going to look at the next protocol in this TCP/IP suite of protocols. In this case, it's the Address Resolution Protocol, or ARP. Now, this is a Layer 2 data link layer protocol. Frames are the Layer 2 component as we send our data down through the OSI model, through the network stack. A frame is what actually commutes across the media, across the network, from one node to the next node. A frame is generated at layer 2, the data link layer of the OSI model, and it is transmitted from a source MAC address, that's a media access control address, to a destination media access control address. Now, the source address is hard-coded onto the sender's network interface card. As the sender is preparing this frame for transmission, all it does is look up his own MAC address and he populates the source MAC address field. However, the source computer must identify the MAC address of the next hop. That would be the next node we're going to hand this frame to on its path to the actual destination. In many cases, that next node, that next hop, is the default gateway or the router that is the node's connection point to all other subnets and segments. In that case, where the destination is on the other side of a router, the local system, the source system, would send out a ARP request for the MAC address of the default gateway. And then once the router hears that request, the router will say, hey, that's me, and here is the MAC address for my network interface card. Now the sending computer can populate the destination MAC address field and then complete the frame by calculating the cyclic redundancy check, which is sort of a crude hash value for verification of completeness, of integrity, if you will, to make sure that the frame hasn't gotten corrupted in transmission. And at that point, the frame is complete. So before we can complete the frame and send that frame out onto this network media, we must populate the destination MAC address field, and that's what ARP helps us do. Now, by the time I get to layer 2 of the OSI model here, as I'm processing my data down through the network stack, I've already identified the destination IP address. And this is where a routing decision has to be made. If the destination node is actually on my local subnet, my local IP subnet, I can hand the frame to him directly. And I'll ARP out for his MAC address. And I'll say, hey, the guy with this IP address 192.168.10.15, for example, I need your MAC address. Well, all the nodes will look at their IP address and say, nope, not me, nope, not me. Eventually, the guy who has that IP address will say, oh, that's me. And here, by the way, is my MAC address. So he responds back with an ARP response that says, I'm 192.168.10.15, and here's my MAC address. Boom, that's how the source can populate that destination field MAC address. Now, once the sender receives that ARP response, he'll cache that information in memory for 10 to 15 minutes, depending on the network operating system you're using. And he'll have it memorized now, so he doesn't have to ARP out for it a second time, because typically you're going to send a destination more than one frame. So I'll memorize it and I'll just pull that out of memory, and I'll only go get a fresh cut in 15 minutes if I'm still communicating with that destination. Now, this lends itself to a particular attack, a vulnerability with ARP, and that is if a bad guy can convince your computer that while he's not really 192.168.10.15, for example, he might convince your computer that he is, and he'll send his MAC address to your computer as an ARP response. And now your computer thinks it's actually sending to the legitimate destination of 192.168.10.15. Really, he's sending his information to the bad guy's MAC address. And so this is called ARP cache poisoning. It's a fairly common and dangerous attack. There still is a vulnerability of ARP cache poisoning, even on today's relatively sophisticated and much more secure networks than they ever were before. So we'll probably take a closer look at ARP cache poisoning later when we get looking at the different attacks on networks. Now here we see the actual network captures as we look at frame 5 on the slide. In the left-hand side, we see that this is an ARP request. And it basically says, whoever has 131.107.2.100, tell 131.107.2.216. And then as we look on this capture on the right, the network capture on the right, analyzing frame number 6, we see a response back that says, I am 131.107.2.216, and here is my MAC address. So here we see the ARP request and the ARP response. This completes our lesson on the TCP/IP suite of protocols. In this lesson, we're going to be covering transmission media and transmission technologies. Network media is this transmission media that I mentioned in the title slide there. The media is the mechanism that carries the signal and data across networks, from the source node, the sender, to the destination node, the recipient. So very often these are cables of some sort, and in our wireless networks, we actually use the air as the transmission media. But let's dive into this and let's talk about these different types of transmission media right up front here. One aspect of the media that we're going to be exploring deals with the efficiency of the transmission. In other words, how far will the signal go before it degrades so much we can't understand it anymore? And the second aspect deals with the security aspects of the actual signal conveying across the media. So as you look at these different media types, it's a good thing to have in your mind what is the more secure and more efficient transmission media, and what is the lesser secure and lesser efficient transmission media. Recognize that more secure and more efficient is almost always going to be more expensive. And the weaker media, the types that are very prone to data theft and data corruption due to interference and static and things along these lines, this is generally your cheaper type of media. So there's always going to be this trade-off. So let's dive into these 5 different types of transmission media, and we'll understand a little bit more about them and how they operate. The first one on the list here is considered to be the most secure because it has essentially no emanations. In other words, it's very, very difficult for a bad guy to steal your data signal as it conveys through the fiber optic cable. And it also is a very efficient transmission mechanism. In other words, it can go miles and miles. before the signal degrades to a point where the receiver can't understand it. So what fiber optic cables actually use is light pulses. In other words, it's actually photons that are carrying the signal and the data. So if you want to think of it in very basic terms, think of when the light is on, that's a binary 1. And when the light is off, that's a binary 0. And photons do not produce emanations. Now, what we're going to see in some of these later transmission media types is they use electrons to carry the data signal. Well, electrons have this phenomenon called emanation, and we'll dissect that in just a minute, but photons don't emanate, and as a result, they're considered to be the most secure. They are one of the most efficient media types, and therefore they're one of the most expensive media types. We get very high data rates on fiber optic cables, gigabits of data, and therefore it's a very good vehicle to carry your signal to use as you connect your locations together across the city perhaps, or even within an office. Now typically it's more expensive than we want to spend within an office. The next one down on the list is coaxial cable. Now coaxial cable has been around for a long time. It's actually commonly used in your homes to carry your TV signal into the home from the cable provider. It is a center conductor that actually carries the data signal, but then wrapped all the way around that center conductor is a grounded sleeve or shield that helps to keep the signal contained within the coaxial cable. Now, as it holds that energy within, less energy leaks out. Therefore, the emanations, the security component of emanations, is fairly strong. Difficult for a bad guy, not impossible though, but difficult for a bad guy to steal that signal without getting very close to the cable, perhaps even placing into the cable itself. Coaxial cable uses electrons and radio frequency waves on that center conductor to convey the data within the signal. And again, it's these electrons and radio frequency waves push electrons around. And as these electrons flow through the cable, they actually emanate an electromagnetic field around the cable itself, outside in the air around the cable. Now, that grounded shield around the coaxial cable tends to keep that collapsed and contained within the shield. However, some will still leak out. So it has very good emanation protection. And however, it still is not emanations free like fiber optic cable. Now, there's another aspect of the emanations, and that is if I can emanate a signal outbound, that says other signals in the area that are emanating might actually induce signal, which is corruption and interference on my signal within the coaxial cable. So these emanations from other sources can actually penetrate into the coaxial cable and start to degrade my signal due to this interference. So coaxial cable is considered one of your better connection media for networks. The next one down on the list is shielded twisted pair, and its very close cousin, unshielded twisted pair. Now, this is your standard Ethernet. Your standard Ethernet almost always uses UTP or unshielded twisted pair. Now, these two are constructed approximately the same, other than the shielded twisted pair has a sort of an aluminum foil wrapping, a conductive wrapping around the wires inside the Ethernet cable. And it's called twisted pair because there are actually 8 wires inside these cables, and we take one wire that's going to carry the data signal and a second wire that is going to be grounded, and we wrap the ground wire around the data wire. In other words, we twist them together as a pair. Now, the grounded wire tends to disrupt this propagation of the emanated field around the data carrying wire. So as we're pushing a signal through that wire, we are using electrons to carry that signal, and those electrons, once again, propagate into the air. Well, again, the grounded wire that's wrapped around it will disrupt that magnetic field around the data carrying wire, and we have some marginal shielding, if you will, because of this grounded wire. Now, the shielded twisted pair is a little bit better as far as emanation security are concerned, but it is more expensive and it's fairly difficult to work with. If you're building these cables, it's a real pain to build these cables. The unshielded twisted pair, hands down, has dominated the marketplace when it comes to connecting your networks together. So the UTP is by far the dominant technology network media that's used for corporate networks. Now, a very popular, relatively new entry into computer networks as a media is wireless networks. It uses radio frequency electromagnetic waves propagated into the air, where the air is actually the media itself. And this means it is the least secure because it is nothing but emanations in the air, which means a bad guy with a receiver can listen to everything you're propagating across your network. That's why we have to take extremely high measures to secure our wireless networks. Because we don't have to buy cables and have cables run throughout the building, this is also the least expensive network media that we could implement as well. So it's very easy to assemble a wireless network. It's very easy to tear it down and move it, relocate it, etc. So the wireless networks are the least secure with nothing but emanations, but it is by far the cheapest approach when it comes to media because there's essentially no cost. We're using the air as the media. And again, as we said, these emanations allow for theft of data signal and also allow for inbound propagation of unwanted signal that tend to degrade the signal due to crosstalk and interference. Now, this term attenuation deals with a signal degradation over distance. We're going to look at that in just a few minutes. This lesson is going to cover several of the key terms that need to be understood about network media. So we're going to be looking at these definitions. Now, the first definition we need to address is a common problem with all network media types, and that's called attenuation. Attenuation is a naturally occurring phenomenon, and basically it is degradation of signal over distance. So as you have a longer cable, and you are transmitting from one end of that cable at the source to a destination at the other end of that cable, the signal will degrade over distance. So the longer the cable is, the more degradation or attenuation there is with this signal. Now, we can make a cable so long that the signal is so degraded by the time it gets to the destination that the destination can't understand what the signal is saying. So we have to move back then to a shorter and shorter cable until we can be certain that the destination will always understand the signal, that it hasn't been degraded so badly that the destination can still understand what the signal is conveying, the data part of the signal. Now, this attenuation is due to several different types of phenomenon. The first one is called interference. This would be some sort of induced signal due to emanations from some other source. It might be a radio tower, it might be a wireless network, it might be a microwave oven that somebody's using in the break room. But electromagnetic interference in the air, it's all around us, is a source of interference. And if that signal that isn't wanted somehow finds itself on our wire that's carrying our data signal, that by definition is the interference. There's a phenomenon called impedance that is a component of high-frequency data signaling. And if there is high-speed data, of course, on our corporate networks, that's what we want, high-speed data, we wind up with some sort of impedance characteristics or phenomenon occurring. Well, the impedance of the system must be very well tuned so that all components have the same impedance. And if there is some sort of mismatch, we wind up with an inefficient transmission through that area. Maybe it's a connector, or maybe the cable got cut and we had to solder it back together, some sort of splice. These are sources of impedance mismatch. And then, of course, as I said, if we have to put connectors together, the electrons running through our cable must jump from a pin on one connector into the wire on the adjacent connector, where these connectors squeeze these pin in the socket together. Well, this minuscule air gap, perhaps even microscopic air gap, is a source of signal loss. And they call this insertion loss. As the pin gets inserted into the jack, then we have this degradation or attenuation of signal. Now, the next definition down is interference. And as I said, interference is generally unwanted signal on your data carrying conductor. And it very often is induced by some sort of emanation from some other source. As we said, it could be a radio transmission tower. It could be you're very close to the airport and the radio communications between the tower and the airplanes around. It could be radar. It could be a wireless network. Many, many sources of emanated electromagnetic energy in the air all around us. If that signal gets induced into our wires, boom, this is interference. Now, we have this superset. It's called electromagnetic interference. That says, of course, that it uses electron flow and magnetism to push those electrons around. And this is the superset category. This is all forms of this interference. However, there's a subset called radio frequency interference, and a key term here is frequency. If there is any regularity to the interference, it's generally considered to be RFI, radio frequency interference. Frequency being frequently presents itself, and it's sort of some consistent pattern of interference. This is RFI, a subset of EMI, electromagnetic interference. And then we have another subset that is more of a transient noise, a very irregular, staticky, no pattern, no regularity to the electromagnetic interference. So things like a lightning strike, or perhaps we turn on a fan that uses an electric motor, and that fan induces some sort of static into our electrical system. This would be a type of transient noise. Again, a subset of electromagnetic interference. This is all bad for your data signal because I want to be able to read my binary ones and zeros out of my signal that's carrying my data. Well, if these signals are inducing themselves into my wires, this is doing nothing but causing confusion and havoc in my attempt to understand my emulated signal and the data that that signal is carrying. We've already discussed emanations to a large extent, but basically this deals with the electron flow through a wire induces or emanates a magnetic field in the air around the conductor carrying the electron. Now that in itself is an emanation. And if it was all by itself left alone in nothing but air or a vacuum, it wouldn't cause us too much of a problem. However, because we have many wires that might be adjacent to one another, like a cable run, a bundle of Ethernet cables running through the walls or through the ceiling, and they're generally packed tightly together, the emanated signal from one wire induces signal interference into adjacent wires because they cross this airspace where this magnetic field is built. So these emanations cause interference and signal degradation. As the second wire gets interference induced into it, essentially that second wire stole energy from the first wire that was emanating. So the signal is being degraded in the first wire due to energy lost in the second wire. And the signal in the second wire is being degraded because it now has electron flow that isn't part of the intended signal. So emanations are a problem in this regard. Further, emanations are the source of data theft. So a bad guy, without actually even touching the wire, can use a detector and sense these electromagnetic fields around the wires and can identify the presence or absence of electron flow, which essentially is your signal carrying the data. So the bad guy can actually steal your data just by sensing these emanated signals into the air. Again, this is a security concern in addition to be a degradation of signal. And as we described these emanations, I also described what is called crosstalk. As I'm sending an intended signal down a wire carrying data, it induces or emanates a magnetic field in the air around that wire. Well, an adjacent wire that penetrates that magnetic field is going to have energy induced into its data carrying signal. And this is called crosstalk. When one wire induces signal, unwanted signal, in the second wire, this is called crosstalk. And this is that degradation of signal and the theft of energy. And again, could be used to steal the actual data. So these are some of our core terms for network media. And these have implications relative to efficiency of transmission as well as the security aspects of the particular media. This lesson covers several more terms related to network media. In this lesson, we're going to be looking at the difference between baseband and broadband media types. Let's first look at baseband. Baseband transmission technologies allow only one signal on a conductor at a time, on the media at a time. And if a second signal is transmitted onto the media while a first signal is present, both signals are destroyed. In other words, the recipients can no longer understand what the data is that the signal is supposed to be carrying. So both signals are destroyed. This is referred to commonly as a collision on a network. So on baseband networks, only one node is allowed to transmit at a time. And if two nodes transmit at the same time, both transmissions are destroyed. Both transmitting stations need to stop transmitting and allow the media to stabilize, and then they can, over time, try to begin to access the media again, hopefully not colliding with somebody else's signal. So we're going to be looking at ways that this may occur later on. Now, one technique to allow multiple nodes to share the same common media for baseband is using something called time division multiplexing. What time division multiplexing does is it takes, let's say, a 1 second period, and it breaks it up into, let's say, 10 different time slices. And it then will allow node number 1 to transmit during 1/10 of that 1 second period. One time slice is what it's called. And then it says, all right, you have to stop. Then it goes to the second node and says, all right, it's your turn to transmit. And now the second node transmits, but the other 9 nodes are not allowed to transmit during that one time period. By using some mechanism of identifying whose turn it is, time division multiplexing allows multiple nodes to share a common baseband media. And the media access methods are commonly used and have been used historically, will be explored in later videos. So, some technologies that use baseband are Ethernet. Now, Ethernet, as we said, is probably the single most commonly used network media for all of our networks. We might have long data runs where we use fiber optics or wireless or SONET or something along these lines. SONET would be fiber optic. But within a building, for example, almost all cabling is Ethernet today. So Ethernet is the champion when it comes to our media type. Earlier media types that used baseband transmission technologies were Token Ring and ArcNet, Advanced Resource Computing Network, or Attached Resource Computing Network. So these two older technologies, Token Ring and ArcNet, also were baseband technologies where only one node is allowed to transmit at a time. Those last two, the Token Ring and the ArcNet, are considered to be token passing technology. We'll talk more about that later. Now, the competing technology to baseband is broadband. Broadband is the newer, rapidly growing technology where multiple data signals can occupy the same common media without destroying the other signals. In other words, multiple nodes can transmit simultaneously on one conductor, on one media type. And so this is called broadband. And as you can probably figure out, broadband, because it allows multiple data streams on a single wire, is much more efficient. It has a much higher data rate. And it's used in larger, faster networks. Now, the kicker, though, is typically broadband technologies are more expensive than the baseband technology. If only one guy is allowed to use the wire, of course, it's slower, and of course, the electronics are relatively cheap and easy. But if I need to squeeze 2 or 10 or 20 or 200 nodes on the same wire simultaneously, you can imagine the electronics that support that system are substantially more complex and therefore more expensive. So broadband has substantially higher data rates, more data throughput in the same period of time, but it is notably more expensive. How do we get those different data streams onto the media and not allow them to destroy somebody else's data stream that's concurrently on that same media? We use something called frequency division multiplexing. Typically, this is a radio frequency, which is electromagnetic waves, a radio frequency wave across a coaxial cable. And this allows for one signal to propagate at, let's say, 10 megahertz, and I can send a second signal, let's say 13 megahertz, and a third signal at 17 megahertz, and a fourth signal at 19.2 megahertz, and I use simply a different frequency for each transmitting station, and of course the destination must be tuned to that same frequency. So now what we're seeing is we have electronics that are not just turning on a voltage or turning off a voltage, but they are actually producing these electromagnetic waves, which are sine waves at a specific frequency, but the destination must be tuned to that same frequency, so we have to coordinate all that. And if you have to operate at different frequencies, you now have a very complex transmitter and receiver series to communicate across this same broadband media. Frequency division multiplexing uses different frequencies for the transmitter-receiver pair, but I can put those differing frequencies on the same coaxial cable. So one cable run, and I'll splice out on the destination side to 10 different nodes, but only the nodes that are tuned to my frequency can understand my signal. The good news is I can put 10 or 20 or 200 different signals on that same coaxial cable simultaneously and share that one cable with many data streams. A newer and also very high efficiency and very expensive broadband technology uses wavelength division multiplexing. Now, wavelength relative to the wavelength of light waves. So now we're using photons, not radio frequency electromagnetic energy. We are using optical energy or photons, light pulses across a fiber optic cable. And as we had discussed when we were looking at the different media types, fiber optics are one of your best media types when it comes to efficiency, the ability to carry multiple data streams using wavelength division multiplexing, the lack of emanations, the lack of interference, the greater distances, and the greater security. So this wavelength division multiplexing over fiber optics is the bomb these days, with very high data throughput. The problem, though, is it is notably more expensive, yet still it is notably more secure. All right, all that said, we've covered these two definitions thoroughly, and we will pick up shortly where we left off. In this lesson, we're going to look at Ethernet. Ethernet uses what we call twisted pair cable. It's a total of 8 wires in one jacket and one cable. We take those 8 wires in pairs, and each pair will consist of one wire that's going to carry the data signal, and this second wire is going to be grounded. And then we're going to twist these 2 wires together. As you can see in the photograph here, we have then 4 pairs of wires that are twisted together. And the grounded wire that's wrapped around the data carrying wire is twisted around that wire so that it will disrupt the electromagnetic field that is emanated as the electrons flow, the signal flows through the data carrying wire. Now, this reduces the emanations. It's not terribly effective at reducing it, but it's better than nothing. And it helps to allow the data run, the cable length, to be greater, and we can still have enough signal at the end of the cable to understand what the signal is. So we use this twisted pair cable for our Ethernet networks. We notice that the connector at the endpoint has 8 pins, and it's called an RJ45 connector. So those pins actually are what plug into the back of your computer in the network interface card and plug into the wall jack, which is an Ethernet cable behind the wall, but it's the female portion of this RJ45 connector. And then, of course, those 8 wires connect to 8 pins that are part of this RJ45 connector. Now, we have unshielded twisted pair, and that is the single most dominant cable type or media type for networks today. All of our data centers have miles and miles of UTP, unshielded twisted pair. And businesses have this UTP in the walls, in the ceilings, etc., that connect all the offices together, back to the wiring closets where the switches and routers live, and to the data center where all the servers live. So that is almost all Ethernet. Now, there's another form of twisted pair called shielded twisted pair. And on the slide, as you can see down below, the very bottom image is a photograph of shielded twisted pair. And what you'll notice is there are 4 pairs of wires, just like there was with unshielded twisted pair, but surrounding that series of 4 wires is a plastic mylar sheet, very super thin plastic sheet, but it has been coated with a very thin layer of conductive material. So we wrap this, it's almost like a foil. We wrap this foil around the 4 twisted pairs, and then we ground that foil at the endpoints. So this produces an extra layer of shielding around the data carrying wires. So this is our shielded twisted pair. Now, shielded twisted pair has better emanations protection, less signal propagates out into the air around the wires, and it has better protective shielding so that emanated signals outside don't induce so much signal into our wires. And it allows for slightly longer cable runs because of the greater efficiency keeping the energy contained within the wires. However, the cost and the difficulty of using STP is so high, the benefits aren't worth it. So if you have emanations or efficiency concerns, STP typically is not your solution because it's notably more expensive and the benefits are only marginally increased. So UTP is by far the dominant technology. As we twist the ground wire around the data carrying wire more and more and more, eventually if you twisted it very, very much, you would have a ground wire that was completely encasing the data signal wire. However, the problem is that consumes a whole lot of material. You just took a 100-meter cable, and because you twisted it up so tightly, it's now worth 15 feet of distance. You really can consume a tremendous amount of material by increasing these number of twists. Well, studies have shown us how many twists per foot it takes to get a certain level of improved performance out of the twisted pair cables. For standard voice, which is like your telephone cabling, it's called Category 1 cable, and it has approximately 1 twist per foot. In other words, the ground wire wraps around the data wire. The data wire is now carrying your voice data, analog type data, once per foot. And so Cat 1, Category 1, has approximately 1 twist per foot and is generally only used for voice. You notice there's no digital signaling, no data on that other than analog voice data. Category 2 has approximately 2 twists per foot, and it generally is good to conduct about 4 megabits of signal, data signal, over about a 100-meter span. Cat 3 is 3 twists per foot. It gives us about 10 megabits per second. Cat 4, approximately 4 twists per foot, 16 megabits. Category 5, which is where many of our networks were installed, gave us 100 megabits. Today, we want greater data rates. So we're looking at gigabit Ethernet. And now we can either use a very highly refined Category 5 called Cat 5e to get 1 gigabit, but Category 6 was intended as the 1 gigabit per second UTP type of cabling. Now, we have 10 megabits baseband using twisted pair, that's 10 base T. 100 megabits baseband, remember baseband says 1 signal per conductor only and ever. If a second signal hits the conductor, we've destroyed the signal. And again, so 100 base T is 100 megabits baseband twisted pair. 1000 base T is 1 gigabit per second baseband twisted pair. There are also cables called crossover cables in Ethernet where these pairs of wires, one pair is typically considered a transmit pair and one pair is considered a receive pair. The cables are built so that the transmitter and receiver pairs are plugged into a hub or a switch, and that's where they connect to the destinations transmit connects to the destination's receive. So the crossover occurs in either the hub or the switch, some central connecting device, and we'll be talking more about these devices later on. So the crossover occurs in this intermediary device, a hub or a switch. However, if I needed to connect two computers directly together, I would buy a crossover cable that connects the TX directly to the RX on the other side of the wire, on the other RJ45 on the same wire. In this case, my TX pair on one endpoint connects to the RX pair on the other connector, and vice versa. My RX connects to the other end's TX. So the crossover occurs in the cable because there is no intermediary device like a hub or a switch. Now, there was another area of concern relative to the jacketing on these cables. Historically, PVC, that's polyvinyl chloride jacketing, is used. And by the way, that's what almost all of our cables are today. However, the problem is it burns at a relatively low temperature, and when it burns, it emits poisonous fumes that will kill people. For fire safety, if there are concerns about the jacketing of the cable, that if it burns, it's going to injure people, there is a jacketing that uses a different chemical that burns at a much higher temperature, and therefore the toxic fumes are not quite so prevalent with a standard fire. And this is called plenum-rated cable. And it really, plenum-rated simply says we use a different chemical for the jacketing, but that chemical burns at a much higher temperature. In other words, it doesn't emit those toxic fumes when it burns so readily. And typically this is what is used inside the walls or in the crawl space if there is a high risk of fire. So this plenum-rated cable is notably more expensive, therefore not commonly used, and in most cases we've come up with solutions where we don't need to buy the plenum-rated cable versus our standard Ethernet cabling. In this lesson, we're going to be looking at the wireless media transmission technology. Just an introduction, we've got a whole section on wireless later. So in wireless networking, the Institute of Electrical and Electronics Engineers defined a specification for wireless local area networks, wireless LAN as they call it. And that specification is defined as 802.11. So the 802 series deals with communications over networks, and the 11 series, 802.11, says wireless networks, wireless local area networks. So that's where this specification comes from. Now, they define the electronics and the radio frequency transmissions, the frequencies that have been allocated by the FCC are utilized and built into these specifications. Signaling schemes, the way we modulate and encode the data into the radio frequency energy that is propagated out into the airwaves as the wireless signal. This is all defined by the 802.11 specifications. Now, what happens then is the manufacturers of wireless access points and wireless network interface cards, they have to interpret those specifications and then implement them in their electronics and the software that controls those electronics. They have to build these radio transmitters and receivers using specific types of antenna that meet the specifications. Frequency controls have to be in place. And so the vendors of the wireless components have to meet these 802.11 specifications as defined by IEEE. And of course, the FCC allocates specific frequency ranges for these wireless networks. Now, the great thing about wireless networks is they are easy to install and they're inexpensive. Why? Because you don't have to buy any cables. You simply buy an access point. Now, you do plug the access point into the Ethernet network, but then the signal is propagated from the access point out to the wireless clients using the airspace. And as a result, there's no need for cabling. So it makes it very efficient. Your users can relocate from one cubicle to a different cubicle. They can go from their office to the conference room, to the break room, whatever they want, and they can still stay connected. This is called roaming in the wireless network. It's a very fast and efficient way to get nodes connected to the core network that is wired. This would be where your servers are, where the resources live, the file servers, the other resource servers, perhaps connectivity to the internet. So we'll connect wirelessly between the laptop, as we see in the slide, back to the access point. And then we use a wired network from the access point back into the core network to get the resources and perhaps even internet connectivity. This is how the wireless network operates. Because the wireless emanates its data signaling into the air, it is least secure. In other words, a bad guy simply has to fire up his laptop and he can eavesdrop on every transmission that occurs between the access point and the client nodes. And it also is most susceptible to interference from other radio frequency sources. So we have these problems that we have to deal with. This is one of the reasons why there are power limitations in those 802.11 specifications that say your access point can only propagate at this power level, trying to contain physically the space that you are emanating your signal into so that you don't somehow interfere too heavily with the wireless networks adjacent to yours, on the floor above and on the floor below and on the offices through the wall. These power specifications in 802.11 specifications help to control that and keep the size of the propagated cell, as it's called, to what we would consider to be a functional local area network, and hopefully not much past that. Again, the primary hardware associated with the wireless network is the access point that typically gets a Ethernet cable attached to it back into the core network, but then it is the connection point for all the wireless clients within its cell. So the cell is the area of radio frequency propagation, physical space, and all the nodes that are associated to this access point. So that's the definition of the cell. We'll be looking at wireless networking a lot more in a later section in this series of lectures. This lesson covers modulation and encoding. Now, this modulation and encoding happens at the physical layer, down at the network interface card, and at the network interface card on routers and on other systems like switches, perhaps. So modulation and encoding is essentially this: the encoding of your binary data in a modulated signal that is appropriate for the media. So let's consider fiber optic cable. A fiber optic cable uses photons to carry the signal, and the signal carries the data. So we could say that if I modulate the light by turning it on to encode a binary 1 and turning it off to encode a binary 0, we have just introduced digital unipolar modulation and encoding. Turn the light on, we have a binary 1. Turn the light off, we have a binary 0. The turning on and off of the light is the modulation, and the encoding is the representation that light on equals 1, light off equals 0. Here we've just identified digital signaling. It's either a 1 or a 0. It's not analog. And it is unipolar. In other words, we have two states. It's either on or it's off. So this is a very basic, fundamental modulation and encoding technique. This again is digital signaling, and it's unipolar because it's either on or off. Now, our Ethernet media also uses this digital unipolar signaling as well. And it uses, instead of photons, it uses voltage, which pushes electrons. So electron flow and voltage are the mechanisms that convey the data signal inside the media that is Ethernet. So with an Ethernet network, we use plus 3.3 volts DC to represent a binary 1, and 0 volts, or the absence of voltage, to represent a binary 0. And I can use this 3.3 volts to modulate the voltage from 0 to 3.3 volts to encode my binary 1s and 0s. Now, I say that Ethernet uses digital unipolar signaling. There are many signaling schemes, and there are some variations on this. So this is an example. It is not necessarily a lot. There is also a bipolar signaling scheme And in my example here on the slide, I'm referring to what we would use over a T1 connection, for example. That's a long-distance signaling scheme used by the telco systems. So back in the days before we had such great internet connections from coaxial cable or fiber optic broadband or whatever you're using today, back in the day, the way we had to connect our offices together was we would pay the telephone company for a dedicated set of wires between the home office and the branch offices. And it used T1 technologies, Telco 1 technologies, which used plus and minus 120 volts to convey its signal. And this was called digital signaling, but it was bipolar. In other words, I could be plus 120 volts to convey a digital 1 or minus 120 volts to convey a digital 0. And the good thing about this is, if you notice, in between each binary bit, there is a return to 0 state. In other words, two ones in a row are clearly delineated because I send you out a binary 1 at 120 volts, but then I return to 0 volts for a period of time. And my second one is coming, okay, here it comes, boom, there's the next 120 volts to convey my second binary 1. Now, over a long distance, those binary 1s are going to attenuate. They're going to degrade. And over some distance, it's going to get to a point where the receiving side is struggling to figure out, was that a 1 or was that I'm still at 0? I can't even tell. And so that's why we did this return to 0 for the definition of a 1 bit, and now that 1 bit is done. And here comes the second 1 bit, and now that 1 bit is done. And then we drop to minus 120 volts to represent binary zeros. So this is bipolar digital signaling. And again, this is just one example of the many forms of bipolar digital signaling that can exist. But this example is roughly out of the T1 era of signaling over long distances. So we use much greater voltages so I can afford a lot greater attenuation because my data runs are so much longer. Now, the third modulation and encoding scheme that we have here is analog signaling. So we had two digital signaling schemes, unipolar and bipolar. Analog signaling uses radio frequency waves to conduct its modulation and encoding to get its binary data tucked into this radio frequency signal. Now, analog signaling, as we said, uses radio frequency waves, which are electromagnetic, and they can propagate wirelessly into the air. It's reasonably efficient to send this radio frequency signal into the air, but we also can send that radio frequency signal through some coaxial cable as well. So the coax can be used for either digital or analog, but the digital cannot be conveyed over wireless. Analog signaling can be used over coaxial and wireless through the air, and is not really good on Ethernet cabling, the other form of media that we were discussing earlier. Now, how do we modulate and encode signal using analog signals? Well, I have got several forms here. The first one is called AM, or amplitude modulation. As we look at that signal over to the right next to the analog label, we see that it has a certain height. That sine wave goes a certain height up. Now, the height of that wave is an indicator of the power or voltage that's applied to create that wave. And what I can do, if I want to encode a binary 1, I can make that wave taller. In other words, I'll use greater voltage, greater power for that one part of the cycle to encode a binary 1, for example. And if I want to encode a binary 0, I will decrease the voltage below the carrier signal that we see there. So a lower power will represent 0 as the encoded signal. And I'll modulate the voltage or the power of this first portion of the sine wave, either higher or lower, to encode a binary 1 or 0. That's amplitude modulation. Frequency modulation says use a higher frequency, would be a shorter wave, to represent a binary 1, and use a lower frequency, a longer wave, to represent a binary 0. So here's another way I can modulate the frequency to encode binary 1s and 0s. Higher frequency, shorter wave equals a 1, lower frequency, longer wave equals a 0. Now, I also can use something called phase shift keying, PSK, and this says where that one sine wave completes, if I continue upward as it's supposed to, as we see in the diagram, that represents no shift in the phase, and that would be a binary 0. But suppose I inverted that wave now 180 degrees, and instead of carrying upward forward as my sine wave continues, suppose I reverse that wave and I go down for a half a wave. And by shifting the phase 100 degrees, I can represent a binary 1. Or if I don't shift the phase, I represent a binary 0. So here is a phase shift keying, another technique for modulating a radio frequency or analog signal wave and encoding binary data bits. This last one, quadrature amplitude modulation, QAM, this is what's used on the bulk of our wireless access points and our wireless network interface cards. It's a combination of amplitude modulation and phase shift keying, and it allows us to encode as many as 64, or the newer QAMs will modulate and encode up to 256 binary data bits in a single sine wave. Phenomenal amount of data packed into a single sine wave. So this is how we're getting these substantially higher data rates, one of the techniques we use to get these substantially higher data rates on our wireless networks. So this lecture has been on modulation and encoding. We're going to break here, and we'll pick up with some new stuff when we come back. Let's continue with the review of network topologies. Now, a topology is a construction, if you will, or a type of construction. And in this case, it's relative to the structure of our networks. Let's first start with the bus topology, because this was one of the original topologies. This came to us out of classically the 10-base-2 and the 10-base-5 type of networks that used a linear bus topology. Now, this is a core backbone. That's the bus part of this that we would snake through the office, if you will, and then you would tap into that bus, that backbone, with the different nodes that you want to connect to the network. Now, the linear bus has the problem that it requires terminators at the endpoint, because here's what happens. As a node on the bus begins to transmit, the energy that is the signal, now this is electron flow pushed by voltage, we're pushing electrons, this electromagnetic energy, this electron flow, will propagate in both directions from that transmitting node on the bus. And if the energy hits the end of the cable and is not properly terminated or destroyed or absorbed, then the energy will reflect back into the cable and begin to destroy the oncoming signal. You remember baseband technology, that's what this is. A baseband technology can only tolerate a single signal on the wire. And if two signals enter the wire at any point in time, both signals are destroyed. Well, that reflected signal is a second signal now on the wire. What we'd have to do is add terminators to the ends, the two ends of the linear bus network. Now, here was a continued problem with this, and that is that if any connection came loose on that linear bus, we now have two halves of a bus. One end is terminated on each half, and the other end of each half is now not terminated. And as a result, we would get that reflected signal due to this unterminated endpoint, and each half of the bus would now be down or non-functional because of this constant collision status. This would cause a constant point of aggravation and constantly needed to be repaired. You'd always be wiggling connectors to make sure that you've got a solid connection on the linear bus. Again, 10-base-2, 10 megabits baseband, 200 meters was the approximate length. About 185 meters was the actual length for 10-base-2. That was called thin net, and then thick net was 10-base-5. It was a fairly large coaxial cable was the backbone that ran approximately 500 meters. About the consistency of a frozen garden hose that you tap into as the backbone or the bus for this network. Now, the next topology we're going to look at is the ring topology, and this was championed in primarily the token ring type of networks. In this case, the coaxial cable switched over to Ethernet type of cable. The token would run from one node to the next downstream node in the ring. So the token would pass from one node to the next, to the next, to the next, and eventually commute the ring. And this was a token passing technique, but the network topology was a ring topology. Now, the next one we're going to look at is called the star topology. The star topology is what we use primarily today on our corporate networks. We wind up with this central connection block. Now, back in the original days, this was really nothing more than a connection box. Basically, it was a series of wires soldered together. There was no power to it. There was no repeater function in it. There was no intelligence whatsoever. It basically connected wires together, and the various nodes would then be able to communicate amongst one another. However, in time, these connector blocks became powered and were amplifiers, or repeaters, if you will. In a digital sense, we would call that a repeater. So in addition to it having all the right connections so that different nodes could communicate amongst one another, that central point that required power was also a repeater that would regenerate the signal. And this formed a star topology because the different nodes would each have to have a cable run back to this central hub or concentrator. Now, today, those hubs have been replaced with switches. However, similarly, each node must still connect back to the switch with typically a dedicated Ethernet cable run. So we still typically today rely on this star topology. The next one we're going to look at is called the tree topology, and this is an extension of the star, if you will. This also could be considered a hybrid topology because it's more a combination of the bus and the star. So here we have the tree topology that has something akin to a backbone, a core, typically high-speed, high data rate backbone that you would snake perhaps up the elevator shaft, and then you would tap off of that backbone on each floor with a star. And so each floor then would be a branch on this tree, with the trunk of the tree being this perhaps fiber optic cable run that would run up the elevator shaft. So this was a sort of a hybrid or a combination of the bus and the star topologies. Now, in this case, if the backbone were to have a failure, then each floor, each branch on that tree would still operate correctly. So we'd have still a functioning local area network for that one floor, but it might not be able to communicate with the other floors in the example that I described. Now let's roll back and let's look at that star. Well, what happens if the concentrator or the hub or the switch in that star fails? So the hub, concentrator, or switch is the central point, the main point of failure. Because if a node goes down, no problem, the rest of the network operates fine. If an Ethernet cable fails, only that one node is affected by the bad Ethernet cable. The rest of the network is fine. So the concentrator itself, or the hub or switch itself, that middle point, is the single point of failure that would bring down the network. On the ring, very similar to the bus, if the ring network ever became disconnected, then the network would be down because the token could no longer commute the ring. So the ring network, the cable itself is the point of failure, just like on the bus, the cable itself is a single point of failure. Trying to defeat this notion of a single point of failure is the reason for the next type of network, the next topology, and that's the mesh. The point of the mesh network is to have redundant paths, and that way if any one cable or device fails, the rest of the network can operate correctly because it didn't rely on that one device or that one cable run for connectivity. There were multiple paths to each destination. Now, the notion of the full mesh is more of an academic model because it typically is greater redundancy than what's really needed, and that increased redundancy comes with a price. And so typically, if you had a second path, a redundant path from point A to point B, you're already great when it comes to redundancy. And you don't need 5 paths because the cost of those 5 paths are way too expensive. So typically that full mesh is more of an academic model and typically not implemented. Therefore, the partial mesh is typically the type of model that has been implemented. Now, the difference between a physical topology and a logical topology primarily comes in the ring topology, because in the early token ring networks, the cable literally was constructed to form something akin to a ring, and the token would pass or commute from one node to the downstream neighbor next node, to the downstream neighbor next node, and would eventually make the entire loop. However, as token ring networks became more and more popular, a concentrator was built so that token ring would actually exist inside the concentrator, but each node would have to have a cable back to the concentrator. So in this case, we had a physical star. The cable runs physically produced a star topology. However, the token passed in a ring topology, but the ring was pretty much collapsed within this central concentrator. By the way, the name of that concentrator was a multi-station access unit called a MAL or an MCEL. We're going to take a break here after reviewing these network topologies, and we will pick up shortly where we left off. In this lesson, we're going to explore the different sizes of networks. This has to do with a little more than just size, though. It has also to do with a level of administrative control and trust. These are some of the aspects we're going to be looking at in this particular description or discussion. Let's first look at this term intranet. This is a collection of well-connected segments. A segment is a network that is bounded by a router. In other words, from the router out to all the nodes that connect to that point on the router, that's considered a segment. And the router can connect multiple segments together, and multiple routers can connect multiple segments together. So this intranet is typically private and has well-connected segments. Now, very often, we will describe the intranet as the network that your computer is connected to, because there's this contrast we're going to bump into when we look at the next term. So consider that this is the network you are connected to. Now, very often, because today data rates are getting higher and higher, you might have a connection to a branch office, let's say, that uses gigabit fiber optic. And as a result, this well-connected notion may fall apart a little bit. So we're going to add two other types of boundaries that establish what we might consider the intranet. And so first, it's this private, well-connected, land speed or better, collection of segments. However, if you have different administration, in other words, a different team is administering the computers on your collection of segments versus their collection of segments, like a headquarters and a branch office with a gigabit fiber optic connection between them, we might consider that because of this different administration, these are different intranets. So this administration, this control and level of trust might define a boundary of your intranet versus their intranet. And yet another component that might tend to be this boundary is security devices. So we have common administrative control and policy. That's one boundary that we might use as our definition of intranet. We have a lack of trust, which is typically going to require some sort of security device added as a boundary, like firewalls. This might be the definition of your intranet. You live on the inside where it's all trusted. Anything outside those security devices are less trusted, therefore not part of your intranet. And finally, we have this original definition that's now kind of getting a little fuzzy because of the high data rates on our metropolitan area connections, regional area connections, and perhaps even wide area connections. This well-connected segment might be skewed a little bit because of these high data rates that we're getting now on our larger or longer runs. To a large extent, it now deals with a level of trust, administrative control, and connectivity. And typically, it is a private entity that holds, controls, or defines policy on this intranet. Now, in contrast to the intranet, we might have a second collection of well-connected segments that we don't trust so much. However, we're connected to it persistently. So this is the classic definition for an extranet. Here we have a less trusted collection, one or more segments that we connect to on a regular basis. Where my computer is attached, it's my intranet. However, I still may have a good connection to this other collection of segments, but that is now my extranet. And the extranet is less trusted, perhaps managed by a different administrative staff, and might be bounded by a firewall or some other security boundary that allows me to filter and limit their access to our trusted environment on our intranet. Now, the extranet has this mid-level of trust and control and connectivity. Even though it still might be that 1 gigabit connection to the branch office, we still consider that that's more of a WAN link and not part of our local area network, our intranet. And finally, the third definition here is internet. Well, that is that big global network that holds all those web resources, the web servers, the FTP servers, things along these lines. Now, that intranet is the public space, and that public space is the least trusted, has the least amount of control from my perspective, and therefore we generally will want to defend ourselves very rigidly from the outsiders coming into my intranet from the internet because of their exceedingly low level of trust. We're going to move forward and we're going to address a little bit more the size of the network. So here's a handful of definitions that tend to describe in physical space how big is the network. We'll start with the smallest and move towards the largest. The first is the personal area network. Now, typically this is about a 10-meter radius. 10 meters is about 33 feet, and therefore this is a fairly small network. So the PAN, or personal area network, primarily will use wireless Bluetooth technology for most of our computing devices, but there's this low-power wireless technology called Zigbee that is very similar to Bluetooth, but it focuses very much on exceptionally low power. So we have very low battery requirements for Zigbee technology, but Bluetooth right now is the dominant technology. Zigbee is coming along, though, in many, many marketplaces. The next one up is local area network. We're talking about tens of meters to hundreds of meters of geographic space. And typically we use Ethernet cabling and wireless networks. This would be our wireless LAN, your typical access point running 802.11a or B or G or N, or the new standard is 802.11ac. And these are our wireless local area networks. So we're talking hundreds of meters that we might string together. And this produces our LAN. And that LAN, of course, as we just described, is kind of like your intranet. Now, the next one down is called a metropolitan area network or a campus area network. And here we're going to take these LANs and we're going to string them together. And we're going to get hundreds of meters to miles to maybe even tens of miles of space out of the metropolitan area network. Typically, these LANs will be connected by fiber optics or perhaps wireless point-to-point connections. And they typically are a metropolitan area network because they have a common administrative force or policy. And that's what makes it a collection of LANs that are connected together. Next one down is regional area network. This typically will run tens of miles and again will run fiber optics and point-to-point to connect perhaps several metropolitan area networks together. The next one down is the wide area network that will run tens of miles to tens of thousands of miles. And this would be what our internet network is like. It is a wide area network. At the same time, the internet is also a global area network. So you can have a private corporate wide area network that is not the internet, but it still may be a global area network because it spans the globe. This wide area network and global area network, they're very similar. However, with some subtle differences, you could have a wide area network that doesn't span the globe, but you then can also have a global area network that does span the globe by definition. So these are sizes of networks related to networking technologies and media. We'll take a break here and we'll pick up shortly. In this lesson, we're going to be looking at different network transmission types. Now, these different network transmission types are defined by the way the network stack and the application that feeds the data into the network stack chooses to communicate with one or perhaps multiple nodes on the network. Now, the first example is called the unicast. The unicast is from a single source to a single and unambiguous destination. This is a one-to-one data transmission or flow of information from one point to a specific single point as a destination. Now, this is typically performed by transmitting from a Class A, B, or C IP address to a destination Class A, B, or C IP address. However, it is also possible to communicate or to send out a unicast to an unambiguous and unique MAC address. However, I'd say that's not as common as from a single IP address to a single IP address. So a unicast is from one node to a specific single destination node, and this is the way many of our network communications occur today. Now, the next one, broadcast, is performed to accomplish sort of network administration. Most of the time, you don't send the actual payload of data in a broadcast, but the broadcast is typically done to achieve some information or acquire some information that is needed to accomplish the flow of data, not actually to perform the flow of data. So a broadcast is typically sent from one node, the transmitter or the sender, to all the nodes within a specified range. And that range is defined typically by the layer 3 address or the layer 2 address that is supplied in the outbound broadcast. Now, you can have a layer 3 broadcast that uses an IP address with the broadcast address for the subnet that you're sending the broadcast to. So that would say all people with an IP address that start with 192.168.10, I'm transmitting this to each and every one of you. So what those nodes would do is every node that hears that broadcast looks at their IP address, checks to see if they're at 192.168.10. something, and if they are, they say, oh, this broadcast is for me, and they process this up the stack to layer 4. They still may discard it at the higher layers, but at layer 3, the expectation is that they will process this packet and hand it up to the higher layers. Sometimes we don't have the IP address information, and we can't use the layer 3 broadcast. In this case, we'll use a layer 2 broadcast, where we use the broadcast address for the media access control layer, the MAC address. We're going to, in this case, for a layer 2 broadcast, supply the broadcast address at layer 2, which is all binary ones. However, if you recall, MAC addresses are typically documented or written by using pairs of hexadecimal characters. And in this case, all ones, the broadcast address, will translate in hexadecimal to all Fs as the MAC address. Now, if you're going to send a broadcast at layer 2, you may or may not be sending a broadcast at layer 3. But if you're sending a broadcast to layer 3, you are always sending the broadcast at layer 2. So a layer 2 broadcast may or may not be a layer 3 broadcast. A layer 3 broadcast will always be a layer 2 broadcast. And basically what you're saying with the layer 3 is everybody within this IP subnet, I'm talking to you. The layer 2 broadcast says everybody on my segment, I'm talking to you. And so here's the difference between the physical segment and the logical address space or spaces that might be assigned to that single segment. The segment is a physical thing. That's the collection of all nodes bounded by a router. However, on that one physical segment, I could have one or more logically addressed IP subnets. That's the assignment of IP address space on that one segment. Then I could have one subnet or I could have multiple subnets on that one segment. The segment is a physical construct. The layer 3 address space is a logical construct where we can type in any numbers we care to on the configuration of those nodes that might all be connected to the same single segment. Now the next one down, transmission type down, is called the multicast. The multicast is from one node, the source server or sending server, to many nodes. that have opted in for this particular multicast transmission. Multicast is defined by the Internet Group Management Protocol and has been allocated a special Class D of the IP address space. Class D IP address space, the first octet number starts at 224 and ranges up to 239. So any IP address that begins with a number between 224 and 239 inclusive, this is a multicast address. And with this one multicast address, I might assign the address to 10 nodes or 10,000 nodes, the same IP address. Let's pick a number. Let's say 230.1.1.5. I can assign that Class D address, that multicast address, to a large number of nodes that I want to send my multicast transmission to. And then from my source server, the one server, I'm going to send out a single data stream to that same IP address, 230.1.1.5. And then every node that has that IP address bound to it is supposed to receive this transmission. It's the routers in between that transmitting server, that source server, and all those destination nodes that have the same IP address bound to it. The routers perform a duplication and distribution process to duplicate these frames, because I'm only sending out one stream, I'm sending out one frame. The routers have to duplicate it to be sure everybody who's opted into this multicast transmission receive a copy of the frame. And this is multicast, again, using IGMP, Internet Group Management Protocol, and again, uses that Class D IP address space of 224 to 239. The opted-in part could be nothing more than you come to my webpage and say you want it, or I might make you authenticate because I only want to send this to my employees, not my competition. So the opted-in can have different levels of security, or perhaps I'm selling you this movie that I'm going to be transmitting, and therefore I need your credit card. I need to hear a cha-ching sound before I let you opt in to my movie transmission. And in that case, once you pay me, then I'll give you the IP address that I'll be transmitting this information to, this movie to. The last one on the list here is called Anycast. Now, this guy hasn't gotten much business yet, but the notion behind the Anycast is we will send a frame from one sending node to one of a set of nodes, and that set of nodes are typically providing a common service. Let's take, for example, DNS, the domain name system. Now, in a corporate environment, you might need one or multiple DNS servers to provide failover and redundancy capabilities. In other words, if one DNS server is down, I don't want to shut down my company. I'll have multiple DNS servers available on my corporate network. So what I'll do is I'll provide an Anycast IP address to all of my DNS servers, and when a client, the one, is looking for the DNS service, he sends his request to the Anycast IP address that is bound to each and every one of those DNS servers. Now, the first one of those that responds to this request satisfies the need. But if the nearest one happens to be down, that's okay, because one of the others that have this same Anycast address will receive my request and will be able to respond to me, maintaining the availability of this particular service. As I said, we haven't been utilizing the Anycast type of transmission yet. However, it may increase as we move heavily onto IP version 6. This is going to conclude our lesson on network transmission types. We'll pick up shortly where we left off. Let's take a look at media access methods. This occurs at layer 2 of the OSI model, the data link layer, and this is where the data link layer is ready to begin transmitting the frame. That's the completed string of binary ones and zeros. That is everything that's required in order to commute this information from the source computer to the destination computer. It's the entire completed frame that has layers 2, 3, 4, 5, 6, and 7 of the header, the payload, and typically a CRC trailer. Now, that's a standard Ethernet frame. That's a standard construction for an Ethernet frame. That's what we're going to be generally using as our example, because that's largely where our networks operate. When we have a shared media, that would be like Ethernet or wireless, we have to be concerned about collision because these are typically baseband networks, which means if two nodes start transmitting at the same time, they will collide. The second transmission will destroy both transmissions, and as a result, nobody's accomplishing anything. You have to stop the network, and then slowly the nodes will begin trying to merge onto the media without colliding again. So because most of our networks are baseband today, we have to find a way to merge these frames onto the wire, the media, without colliding. And that's what we're talking about, media access methods. Now, historically, mainframe computers were the only intelligence on the network, and they would be communicating with many different dumb terminals. Thin clients or dumb terminals. These were the two names for the workstations where the workers were that were accessing the intelligence, the programs, and the data that were existing on the mainframe computer. So back in the day, there was only one box on the entire network that had any intelligence, and that was the mainframe. And so the way the mainframe would manage the media access is the mainframe, the only guy with any smarts, would poll the different thin clients or dumb terminals and say, node number 1, do you have something to transmit? No, you don't? Okay. Node number 2, do you have something to transmit? Oh, you do? Okay, tell me, stop. Node number 3, node number 4. And it would simply poll each of the workstations to see if any of those workstations had something to transmit or not. Now, this was terribly inefficient because you'd have 4 nodes out of 20 that had work to be done, and the other 16 had no work to be done. And as a result, the polling process would occupy time, in this case, 4 out of 5 times polling a workstation that had no work to be done. So it was a waste of time. Terribly inefficient. We don't use it much today. Later technology was token passing, and this was the ARCnet was a token passing network, and token ring and token bus were 2 other forms of token passing network. And in this case, typically the first node on the network would be called the token master, and its job was to put one and only one token on the network. Then that token would pass from one node to another, to another, to another in some sort of programmatic process or sequence, and only the node that was holding the token would be allowed to transmit. All other nodes were not allowed to transmit. So this was another way to avoid these collisions. Polling and token passing were called deterministic media access methods because it is determined absolutely who's going to be transmitting, and there is no contention for the wire. There's no possibility of a collision on the media. So these were deterministic and contentionless media access methods. However, there's an awful lot of wasted time with these 2 different technologies for accessing the media. Where we have evolved is primarily using carrier-sense multiple access, collision avoidance, or collision detection, CSMA-CA and CSMA-CD. Now we're going to take a closer look at these 2 different media access methods. These are the ones that we use primarily today on our local area networks and then some. Now the first one we're going to look at is CSMA, carrier-sense multiple access collision avoidance. This was used in the early AppleTalk days because early Ethernet networks were half duplex. In other words, a node could either transmit or a node could receive, but could not do both at the same time. So when a node is transmitting, it could not tell if there was a collision. And if a second node started transmitting and collided, both nodes, since they're both in transmit mode, would just continue transmitting, wasting time on the network, and as a result, terribly inefficient. So we shifted away from these half-duplex networks to full duplex that were much more efficient and allowed us to get away from these collision avoidance techniques, which also increased the higher overhead. Now, our early wireless networks also operate in half-duplex. In other words, they can transmit or they can receive, but they can't do both. So the early 802.11, 802.11b, and 802.11a and g all operated in CSMA-CA collision avoidance with the higher overhead. Let's look at the timeline of how this CSMA-CA operated. First, we would have a contention period where anybody could transmit, but coincidentally at the moment nobody is transmitting. So a node would listen before talk, would wait, that's a clear channel assessment, and if it senses that nobody is transmitting, it would send out a tiny little announcement frame. Now, the reason it was tiny is because something that small is hard to collide with. It's harder to hit something that's tiny than it is to hit something that's big. So send out a tiny little announcement frame and hope you can get it on the wire before somebody else collides with it and destroys it. And if you can get your announcement frame on the wire, media I should say, then we have this little bit of a wait period to make sure nobody collided with it, but then you have reserved the media for the duration, whatever your announcement frame declared. Now we've moved into a contention-free period, and only you are allowed to transmit because only you had that announcement frame successfully announced on the media. So now you'll transmit your frame, and in wireless, we have a positive acknowledgement for each transmission. So after you transmit your frame, there's a short wait period so that we let the airwaves settle. And then we have still a reserved period for the recipient of that frame to acknowledge receipt of the frame, a short little wait period after that to let the airwaves settle. And then we move back into a contention period where anybody can transmit. So this is the nature of CSMA-CA. With the early announcement frame, a wait period, and then at the tail end of the frame, a wait period, a positive acknowledgement, and another wait period. Those announcements and wait periods and acknowledgements are all not productive time. I'm not actually sending any worthy data. This is all just overhead. So this isn't the most efficient technique. However, because we were operating in half duplex, this was the best we could accomplish to try and minimize the collisions. In contrast to CSMA-CA, we have CSMA-CD collision detection. This is where we recognize there is a potential for collisions, but because we're running now in full duplex, I can sense a collision the moment it happens. So here I am transmitting, somebody miscued and starts transmitting while I'm transmitting, boom, we have a collision. Both data sets now, data streams are destroyed. But because we are running in full duplex, we both can recognize, oh my goodness, we have a collision, stop transmitting, let the dust settle, and now slowly we'll begin this contention period again and we'll start transmitting again. So because we're full duplex with Ethernet, our newer Ethernet, as of about mid to early 1990s, most of our networks started shifting towards full duplex. Because we can sense and transmit at the same time, we can operate in collision detection. Our newer wireless networks that use multiple transmitters and multiple receivers that can sense and transmit at the same time, 802.11n and 802.11ac using this multiple input, multiple output or MIMO technology can sense and receive, therefore they can operate in full duplex. It's up to the vendor that builds these, how they actually implement these access points though. They could potentially run in CSMA-CD. So here's the way this guy works, and it's a lot simpler and a lot more efficient. We start with a contention period where anybody could be transmitting. And if I have something to transmit, I do my clear channel assessment. This may also be called a listen before talk. And I sense the wire media and see if anybody's transmitting. If nobody's transmitting, I simply start transmitting my frame. And because I could sense a collision, I'm okay continuing to transmit because I'm not blind. But if everybody's behaving themselves, my frame will complete correctly. And as long as each node has heard my transmission of my frame, they know not to talk because their clear channel assessment will say, no, the media is busy. So we have a contention-free period for this time. Then after my frame is complete, there's a little wait period, a little fixed period where we're letting the dust settle, if you will. And then finally, we roll into a contention period again where anybody else could sense the media and potentially transmit their data. So these are our media access methods. We talked about polling, we talked about token passing, we talked about carrier sense, multiple access collision avoidance, and finally carrier sense multiple access collision detection. We'll take a break here and we'll come back with our next lesson. In this lesson, we're going to start to analyze some of the components that establish our network infrastructure. These would be the core pieces of our network that make the network actually function. So let's dive into this and see where it takes us. In this diagram, what we see are a handful of different definitions that are going to be critical for our continued discussion and study of networking infrastructure. First, what we see in the middle here is something called a router. Now, this is a layer 3 device that operates at the network layer of the OSI model. And basically, this is the guy that connects our segments together. As you can see, we have a segment that spans off to the left of the router, a segment that spans off to the right of the router, and another segment extends upward from the router in this diagram. So the router and the one interface on the router that connects to each segment defines the segment. So the segment on the left is the network interface on the router, and then all the nodes on that left segment that are attached together through hubs and the bridge that's there in the middle. That is the mechanical, physical construction that is a segment. Now, the hubs are connection devices. They typically aren't used today. However, they were part of the original networking infrastructure. Today, these have all been replaced by switches, but we'll be covering those details shortly. They are a centralized concentrator, and we establish a physical star on the network topology from that hub. So we have one cable that connects directly from the hub out to each discrete node. So that's one cable. Separate cable for a second node, third cable for a third hub, etc. And as a result, these devices all now live on this same segment. Now, the segment that we see here to the left of the router also includes something called a bridge. Now, the bridge is a layer 2 device, and the layer 2 device finally has some intelligence and does some filtering based on MAC address. The bridge was an optional component on a segment, wasn't really required. However, if the segment got too populated, too busy with nodes and traffic from those nodes, then we would have to break that segment in half by placing a bridge in the middle. And this would reduce the amount of traffic on each half of the segment now. Now, with the bridge in place, this still is one contiguous segment. So from the network interface card on the router, through the first hub on the left, through the bridge, through the second hub on the left, and to all the nodes that are attached to those two hubs, this is one segment, and it is a physical construct. Now, we can assign some IP address space. IP is a layer 3 protocol, and it is a logical assignment of IP address to each and every one of these nodes. In this case, in this example, we have the IP subnet of 192.168.10.0 with a /24 mask. Now that /24 mask is its subnet mask, and it defines a subnet mask that equates in dotted decimal form to a 255.255.255.0. If I wanted to, I could assign a second subnet to this same segment. So I would take, let's say, 10 of the nodes on this segment, and I might give them a 192.168.200.0/24 subnet address. And this would be a single physical segment, but could contain one or more, as I just described, logical subnets. The subnet, again, is that logical assignment of the IP address space to the nodes that occupy this segment. All right, so there's some key definitions there. Now, the next thing we need to understand are the couple of terms down towards the bottom of that particular segment, and that's the difference between a broadcast domain and a collision domain. Now, as you recall, I described an overpopulated segment with too many nodes and too much traffic on the segment. And we started getting broadcast storms or collision storms, and this became a very inefficient segment as the population and the traffic on this segment increased. And if we got to the point that efficiency was so bad, the users were starting to complain performance was bad, our solution was to reduce the number of nodes on each half of the segment and isolate these two halves, separate them with this device in the middle called the bridge. Now, the bridge is a layer 2 device, does filtering based on MAC address. And we'll be studying a little bit more about the bridge in a minute, but basically, a node on the left-hand side of the bridge might send out a frame onto the segment. However, the bridge would look at the MAC address, the destination MAC address, and would know whether the destination is on the left side of the bridge or the right side of the bridge, and would only forward that frame to the right side of the bridge if the destination was on that side. If the destination was on the left-hand side of the bridge would simply discard the frame and would never populate the right-hand half of the segment with that transmission. So we reduced the amount of traffic on each of those two halves. Now, this broke the segment up into two different collision domains, because there is no way that a node on the left could ever transmit a frame that would directly collide with a frame transmitted on the right of the bridge on that same segment. Because the only way a frame from the left would ever make it to the right-hand side of the bridge is if the bridge captured the frame, stored it, and then logically, if it concluded it needed to be transmitted to the right half of the segment, it would then transmit the frame to the right half of the segment. So the left-hand node never directly communicated with the right-hand node. It only ever communicated through that intermediary bridge. If a collision was to occur from this transmission, it would be the bridge that collided with the frame on the right-hand half of the segment. So we took one segment and broke it into two half segments called two different collision domains. Now, this tended to reduce the amount of traffic on each of the two halves of this one segment. The next component we would need to talk about is this broadcast domain component. And in this regard, when a node on the left would transmit a broadcast to the layer 2 broadcast address, which is all Fs. If you recall from an earlier lesson, a broadcast address at the layer 2 is all ones, which translates in hexadecimal to all Fs. Well, the broadcast at layer 2 says send this frame to all MAC addresses on the segment. Well, the bridge says all MAC addresses. Well, that includes all the guys on the left side and all the MAC addresses on the right side of the bridge. So a broadcast sent on either half would be transmitted eventually through the bridge to the other half. So all the nodes on this segment, including that one interface on the router, would receive that broadcast, no matter what node it was transmitted from on the segment. So we still had one contiguous segment, one contiguous broadcast domain, but we broke the segment up into two different collision domains. And then on top of this segment, we could, through logical controls, through the IP address space, we could assign one or more logical IP subnets. We'll take a break here and we'll pick up with this definition or description of the networking infrastructure, segments, subnets, and other components relative to the networking infrastructure. Continuing with our definitions here, let's look at the segment. As we said from the preceding lesson, the physical media, the connectors, the nodes, and even the network interface card on the router that is the default gateway for that segment, this defines the segment. So the router is the boundary of the segment. It will typically have one IP subnet, which is a logical assignment of the IP address space, because I could choose 192.168.10.0/24, or I could use 10.10.10.0/24. It doesn't matter to the network which of those number schemes I choose or which of those IP address spaces I choose. I can just logically choose them from the private address space and assign them to the nodes on the segment. I could also bind a second IP subnet address space to a series of nodes on that network, and then I would have multiple subnets on a single segment. So the subnet, as we said, is a logical address assignment applied to the nodes on a segment. And the example here is a 192.168.10.0 with a /24 mask, which equates to a 255.255.255.0 subnet mask. And again, you can assign multiple IP subnets to different nodes on the same single segment. As long as your router understands what's going on, as long as your router has both IP subnets associated, we can route from one of the subnets to the other subnet on the same segment. We talked about the collision domain. A collision domain is bounded by a layer 2 device or a layer 3 device. So the layer 2 device is the bridge, the switch, and the layer 3 device is a router. Now what this says is if a node transmits a frame onto the media, which is the segment, that transmission, that frame, will transmit all the way up to one of these three devices, the bridge, the switch, or the router. It will impact the interface on the bridge, the switch, or the router that the same transmitting node is attached to. However, it will not commute that frame immediately to adjacent connected segments or other parts of the segments. These devices do what's called store and forward in most cases, and the bridge, for example, would receive the frame, store it in memory, analyze the MAC address, specifically the destination MAC address, compare it to his MAC address table that he has stored in memory, and then make a forwarding decision whether or not to transmit this frame to the next piece of the segment or whether he can discard it. It depends on where the destination is. The same with a switch. Now, the router would look at layer 3 information before making that forwarding decision. And so it also would be that store and forward device that would never allow a frame on the left-hand side to be transmitted automatically to the right-hand side. It actually is the router that would be transmitting that frame to the right-hand side. And as a result, it would be the router on the right-hand side that would be the source of a collision if such a collision were to occur. So these three devices, the bridge, the switch, or the router, are all devices that establish the boundary of a collision domain. But the layer 2 devices, the bridge and the switch, will always forward broadcasts. A broadcast is to every MAC address, and therefore these devices that forward based on MAC address say that every MAC address includes the ones on the other part of the segment. While they would be responsible for the collision, not the transmitting node of the broadcast, but the bridge or the switch itself would be the transmitting node to the other portions of the segment. They would be responsible for the collision, therefore they are the boundary for the collision domain. But because they are forwarding the broadcast to those other adjacent pieces of the segment, they do connect these two broadcast domains together. And as a result, it is one contiguous broadcast domain with the bridge or the switch in the middle. Now, the router does not forward broadcasts. So the router is the boundary for the broadcast domain. And remember that the network interface card on the router that is attached to the segment we're describing is also part of that segment and part of that broadcast domain and that collision domain. It is just another node on that same segment, and as a result could be part of a collision or something on that segment, but does not forward those frames directly. Therefore, is the boundary for both the collision domain and the broadcast domain. Now, one more definition we need to look at here is the term called the socket. In the early days of networking, we didn't use the internet protocol. It was just being developed, and our networks operated based largely on MAC address and some other addressing schemes that were encoded into the network interface cards. However, as IP addressing became popular, the term of the socket also became a requirement for understanding if you're going to be working on these computer networks. So the socket is the IP address followed by a colon and then the port number of the service you're looking for on the computer with that IP address. So the IP address or the socket itself describes the major network, the subnet, that's a smaller network, the specific host computer on that major network and subnet, and even the service requested on that particular host. So this got all the way down to not only am I trying to get to that subnet and that particular host on the subnet, when I get to that host on the subnet, I'm looking for DNS name resolution, or I'm looking for a DHCP address lease, or I'm looking for server message block server, a file server in the Windows world. That port number defines the service, but the network address, the host address, and the port number collectively establish something called a socket. And if you wanted to refer to the bidirectional socket, the socket would include the source port number as well as the destination IP address and destination port number. So a fully addressed socket would include both source and destination components. Now that we've got these definitions under our belt, we've got a good foundation to move forward. We'll take a quick break here and we'll pick up where we left off. Let's continue our discussion of the network infrastructure by looking at layer 1 or physical layer devices. Devices would be hardware that are used to build this network. So layer 1, the physical layer, as you recall, has no logical filtering or intelligence capabilities. There's no decision making, there's no analysis. Basically, anything at layer 1 only understands binary bits. It hears a binary 1 in one side and it retransmits it on the other side. It doesn't understand what that bit is or means or what it's a part of, whether it's a SMTP protocol or some other protocol. It has no understanding whatsoever. It simply deals with the binary bits. So a handful of the devices that operate at layer 1 would include the network interface card, and I always call this a NIC to keep it short and sweet. So if I refer to a NIC, that's what I'm talking about, a network interface card. Now, all the nodes that are attached to your network must have a NIC, and that would include the infrastructure components like routers and switches and things along these lines. They have to have some electronics that connect them to the media that perform the modulation and encoding of the binary data bits that are the signal and the data that you're transmitting from point A to point B on a network. Now, the network interface cards attach the node to the network and also are uniquely identifiable. They use a 48 binary bit MAC address, Media Access Control address. Those 48 binary bits are typically represented in 6 pairs of hexadecimal characters. And those characters are generally separated by either a space, a colon, a dash, something along those lines. There's no real standard on what you use to divide those pairs of hexadecimal characters. So don't be surprised if you see colons versus dashes versus just spaces. The next layer 1 device down we want to talk about is called a concentrator. The concentrator was the first centralized connection point for the star topology. The concentrator was unpowered. Basically, it was simply wires connected together. There was no need to plug it into any electricity. There were no blinking lights. There was no repeater functionality. It basically was a connection box. And then each node would be connected using the proper media to the concentrator. An example of a concentrator was the token ring multi-station access unit, was commonly called a MAU or an MSAU. MSAU, and again, unpowered, no repeating capabilities. As a matter of fact, they were mildly famous for degrading your signal because of something called insertion loss. Now, the media itself, this would be your coaxial cable in a 10-base-2 network, the BNC connectors and the BNC terminators. These are part of the media. Ethernet cable, that's UTP and STP. The fiber optic cable, and even the air when we're talking about wireless communications, these components are our media and they are physical. The next one down is the repeater. Now the repeater placed the concentrator. The repeater was a concentrator, but it was powered and it regenerated the signal. So the repeater defeated attenuation. In other words, a node would transmit a frame, a series of ones and zeros. That series of ones and zeros would commute through the media to the repeater, and the repeater would regenerate those ones and zeros because the attenuated ones and zeros were difficult to understand. It would create brand new square and tall and straight and full size ones and zeros. In other words, it would regenerate the signal to a clean, fresh signal. Now, the hub that did replace the concentrator had the repeater built into it for digital signaling. Side note here, the repeater generally was referred to for digital signals, and an amplifier is generally the term used for radio frequency or analog signals. So the amplifier did the same thing the repeater did. It generated the analog signal that it heard. It would listen on one side and hear the radio frequency signal, and it would simply regenerate that signal on the other wire to regenerate it so that we could extend the data run longer. Again, the hub replaced the concentrator. It had a repeater built into it. Typically, they were digital in most cases. Then another layer 1 device is the wireless access point. That is radio frequency radios for transmit and receive, and the antenna components of the wireless access point are all physical layer devices. Now, the wireless access point also performs a bridging function, and as a result, we'll see this wireless access point also when we look at layer 2 devices next. Layer 2 devices will start with the bridge. As we've already said, the bridge memorizes MAC addresses on each of its ports. When we plug the bridge into a segment, we'll have a left-hand part of the segment and a right-hand part of the segment, for example. And the cable that plugs into the left-hand part will have multiple nodes attached to it. And what the bridge does is it memorizes the source MAC address that it hears on that left-hand port. And it builds a table of MAC addresses on that left-hand half of the segment. It'll do the same thing for all the source MAC addresses on the right hand of the segment as well. It'll build a separate MAC address table, and it will memorize all the MAC addresses that reside on the right hand half of the segment. And now, when a node on the left hand side of the segment transmits to another node, the bridge will receive that transmission, because all nodes on the segment will receive that transmission. And it'll look at the destination MAC address. And if the destination MAC address is on the left-hand part of the segment, because the source and the destination are both on the left-hand part of the segment, the bridge doesn't ever forward that transmission to the right-hand part of the segment, reducing the amount of traffic on that right-hand part. However, if the source on the left-hand part of the segment is transmitting to a MAC address that the bridge knows is on the right-hand part of the segment, the bridge would store that information, the entire frame, and then when media access methods would allow, the bridge would forward that transmission over to the right-hand half of the segment. It broke the segment in half, and the goal was to reduce the amount of traffic and nodes on each half. And it made our networks operate a little more efficiently. Now, back in the old days, these were very expensive devices. They typically only had 2 to maybe 4 ports, and it would cost thousands of dollars to buy these things. And we used them sparingly, only when we needed to. Now, because a broadcast will always be a layer 2 broadcast, the MAC address for the destination of a broadcast is always going to be all Fs. That says send this frame to all MAC addresses. Well, because all MAC addresses includes those on the left-hand side and those on the right-hand side, the bridge will always forward all broadcasts to both sides of the bridge. We'll take a quick break here and we'll pick up with the networking infrastructure lecture in just a few minutes. Picking up where we left off, we're looking at the functionality of a bridge. And again, a bridge is placed within a segment to break the segment in half. It's still one complete segment. It is still one complete broadcast domain, because the bridge forwards all broadcasts. It separates the segment into 2 separate collision domains. Now again, the way the bridge functions is it listens to the source MAC address on each of its ports. In this particular diagram, I have a bridge with 2 ports, on the left-hand side and one on the right-hand side. So it will have 2 separate MAC address tables, one for all the source addresses it hears on the left-hand half of the segment, and one for all the source MAC addresses it hears on the right-hand half of the segment. You can see the MAC address tables shown above the bridge, one on the left and one on the right. Well, if a node on the right-hand half sends out a transmission to a destination MAC address that is on the right-hand half, the bridge will recognize that, and it will filter that and not forward that frame over to the left-hand half. So I've reduced the amount of traffic in this particular example on the left-hand half. Now, if a source on the right-hand side sends a frame to a destination MAC address that the bridge knows is on the left-hand side, then the bridge knows that it has to forward that transmission, that frame, to the left-hand half of the segment. So again, we've reduced the amount of traffic on each of the 2 halves, and this made the networks operate more efficiently when they had previously been a little overcrowded. Now, an extension of the bridge is a device called the switch. Back in the old days, that 2-port bridge that we just described might have cost $2,000 or $3,000. They were quite expensive. However, as the price of the electronics came down and down and down and down and down, we found we could replace our hubs with switches that operated as a bridge on each of the ports. So now instead of having a bridge connected to a hub that connected to 24 other nodes, we have the switch that replaced both the bridge and the hub, but now each node is bridged into the network independently. The bridge still memorizes the source MAC address for each port. And in this case, it typically is a one-to-one mapping now. So most of the ports on the switch, which has now replaced the hubs on our corporate networks, most of those ports simply have to memorize one MAC address, the one node that is attached to port 27, for example. We have much greater performance and capacity, if you will, on each of our segments because of the implementation of these switches replacing the bridges. So all of the hubs, to the best of my knowledge, I haven't worked on a network for a long, long time that had any hubs left. All of the hubs have been replaced today with switches, which basically is a bridge to each and every port, and one port typically connects to one node. Now you do daisy chain these switches together. So you will have one in port and one out port as you daisy chain switches together. Those will have a very large number of MAC addresses that it has to memorize. However, typically the bulk of these ports would only have one node attached to them, and therefore it makes for a very efficient transmission. See, when the switch is communicating from, let's say, port 3 to port 27, only those two nodes recognize that the network is busy. The other devices that are attached to that same switch are unaware of the transmission because they are disconnected from the backplane at that point, the backplane in the switch, and they think the network is available. So if they are listening before talk, doing their clear channel assessment, they think the network is free and they begin transmitting. So what these devices do now is they store that transmission and wait until the backplane is free, and then they will make the connection to the right port and forward that frame to the one and only one destination port. The rest of the ports on that switch are completely unaware that a transmission ever even occurred. Now, because we've moved from layer 1, the hub, to layer 2, the switch, layer 2 now has some intelligence. It has some electronics and it has some programmatic smarts. So we can now add specialized, largely security-related applications and management to the switch. See, the hub had very basic electronics. Basically, it was a repeater. It was a connection box and a repeater. Well, the switch has filtering capabilities, so it has to have some computational capability, some CPU, and some program that applies that filtering logic. Well, if we can do that filtering and run those calculations, we can add other programs and applications, features, if you will, that provide us other benefits on our network. So what we're going to see is, since we have the switch connected to each and every port discretely, each and every node discretely now, we can add specialized filtering capabilities to these ports and begin to manage our nodes a little more efficiently and also implement security controls to keep our network more secure. Now, another layer 2 device is the wireless access point. As we said, the wireless access point is a combination of a layer 1 device, that's its radios, the transmit and receive radios, and its antenna. Those are physical. However, because the wireless access point bridges between wireless nodes and between wireless and wired nodes, there is a bridging function, which is a layer 2 function. So the wireless access point also operates at layer 2 of the OSI model. And now a third device that operates at layer 2 of the OSI model is a modem. Now, these don't get much use anymore. These were used in the early days when dial-up over the analog telephone lines were the only way you could connect one computer to a different computer. This was before we had really a full-blown internet that people were attached to. And basically, you would need to know the telephone number for a computer that was also configured with a telephone line and a modem. Now, that term modem is a combination of modulate and demodulate because our computers spoke in digital terms, ones and zeros, but we were transmitting that digital signal over an analog telephone line. So it was modulating and demodulating to communicate with a remote modem across standard analog telephone lines. Why don't we take a break there and we'll pick up with other networking infrastructure devices. Continuing our discussion of network infrastructure devices, we're looking at the switch, a layer 2 device. As we said, a layer 2 device must have some sort of CPU and must have some application program to perform the logic of filtering based on MAC address. And because we have a CPU and the ability to store and process a program and the data that's flowing through the switch, we can now add additional security type of applications as well as management type of applications to that switch. And now we have much greater control, much more granular control over the network infrastructure through applications on the switch. Now, these are extra components that are added to this layer 2 device that provide additional capability and functionality. It still is at its core a switch, a layer 2 device. But we're adding increased intelligence, increased capability, increased functionality that may sound like something above and beyond a switch. Recognize it's still a layer 2 device. It's a switch, but it's been educated and elevated a little bit. It's still a layer 2 device. Now, this lecture is about the VLAN functionality, a significant improvement in security because of the popularity and the very routine implementation of the switch as the core component for attaching your nodes to the network. Now, because we have intelligence associated with each and every port on the switch, if our switch has the capability, and most of them do, many of them do, especially the enterprise grade switches, we can logically assign segment type of information. In other words, while the switch used to be the thing that held a segment together, and any node that was physically attached to the switch was part of the same segment, because of its physical connection, we now can logically, through administrative controls, define that some of these nodes I want to be segregated from other nodes. So I can take a segment that was defined by the switch and bounded by a router, and I can now logically break that up so that a broadcast on one VLAN, these are called virtual LANs, that a transmission on one VLAN is never heard by a node on another VLAN, unless, of course, it goes through the router. So we can say that in this example, we have the red VLAN and the blue VLAN. These are logical assignments that I'd go into some administrative or management console on the switch, and I would say these ports are going to be red VLAN and these other ports are going to be blue VLAN. And there are different implementations of how this actually operates. It could be done by MAC address, but typically it's done by the port number itself. We could say that ports 1, 2, 4, 5, and 6 are red VLAN, and they are going to be logically isolated from ports 3, 7, and 8. Now, I've logically segregated these so that if anybody on the red VLAN, like port number 1, if that port number 1 sends out a broadcast, remember the switch transmits all broadcasts to all nodes in the switch. Now, because of the VLAN functionality, that broadcast on the red VLAN will only be transmitted to the nodes on the red VLAN and not to the nodes on the blue VLAN. So here we have segregated the red nodes from the blue nodes, at least at the broadcast level. And I can assign further restrictions between the red VLAN and the blue VLAN if I care to. And again, assuming that the software in the switch supports it. So again, it's a matter of the specific implementation by the vendors. The only way that a red VLAN node could communicate with a blue VLAN node typically is that I would use different IP subnets for the red VLAN nodes and a different IP subnet for the blue VLAN node. They would both point to the same router interface, and I'd have two IP addresses on that router interface. One that was compatible with the red VLAN and one that was compatible with the blue VLAN. And then red VLAN would send the frame to the router would make a routing decision and put that frame right back on the same wire, only now it's to the destination IP address for the blue VLAN. So the routing function would have to kick in. That's a layer 3 function. And the forwarding capability would not be through the switch based on layer 2 data, but through a router based on the layer 3 data. So this is the VLAN functionality of a switch, a layer 2 device, one of the core components of your networking infrastructure. Now, looking at layer 3 network devices, we get to the router. This is one of the core components of your network as well. So the switch and the router, I would say, are your two primary devices. Another device that's coming up quickly is the wireless access point. But the switch and the router are, I would say, the top two guys in your network infrastructure. Now, this guy is smarter than the switch. He understands some layer 2 information, he understands some layer 4 information, but primarily he focuses on layer 3 data, the IP address, as we typically use today. He can be configured as a firewall. That's another great feature of the router, is I can assign something called an access control list, an ACL, to the router, and I can prohibit certain types of traffic based on IP addresses and based on ports and protocols. So I can limit traffic flow filtering through the router. Now, the router, as you recall, is the boundary for a broadcast domain. He does not forward any broadcasts. Each interface on the router will participate with broadcasts for the broadcast on that segment, but will not commute those broadcasts to other interfaces. So he's a boundary for the broadcast domain. He also is a boundary for the collision domain, because if he is going to forward a packet at layer 3, he will store that packet and then forward that packet on to the next segment when media access methods allow. So again, he is a boundary for both broadcast domains and collision domains. Now, some routers, and typically these are done on larger scale networks, do something called cut-through that is different from the store and forward I've been describing. So there are some exceptions here, but fundamentally, for your level of understanding right now, consider that the router is a store and forward type of device. It stores the information, then can process it, and then would make a decision about forwarding or not forwarding appropriately. The router has to be taught what the network architecture is like. And here we're talking about the logical address space that gets assigned to the physical subnets. So as we attach Ethernet cables to the port on a router, and the other end of that Ethernet cable connects to a switch to establish the segment, we would also assign an IP address space, or IP address specifically, to that port. Now that defines the address space for the segment. And in this way, we teach the router about the IP subnets that the router is attached to. However, very often we'll have multiple routers in our environment, and we will need to teach those different routers about the networks that can be connected to through other routers. And this is a definition of either static routing or dynamic routing, because the router will hold this table in its memory so that it can make the appropriate forwarding decisions. We have this route table that is established in the router, and we'll talk about either static assignment or dynamic assignment. And we'll talk about some protocols that are used so that the routers can teach each other dynamically about all the networks they know about. Now we're going to take a break here, and we're going to pick up with layer 3 network devices in our network infrastructure. Here we're continuing our discussion of network infrastructure, in this case specifically layer 3 network devices, and we're looking at routers. So as we said, a router is a device that connects different segments together, and each of those segments will typically have at least one IP subnet associated with it. And a router knows about the subnets that it has nodes, that it has network interfaces attached to. So as we look at the diagram on the right-hand side of this slide, we see that router A in the upper left-hand corner there has a network interface on 192.168.10, and his IP address is 10.1. He also has an interface on 192.168.12.1, 192.168.11.1, and 192.168.15.1. So router A knows about those 4 networks because he has those .1 interfaces on each of those IP subnets. However, router A doesn't know anything about the 13.0, 14.0, 16.0, 17, 18, 19, 20, 21.0 networks that are attached to other routers B, C, and D. So we have to teach router A that if one of the nodes on one of his subnets, 10, 11, 12, or 15, want to communicate with, let's say, a node on the 19 subnet, router A has to know a path to get to that 192.168.19.0 network. So we have to teach him using a specific command if we're going to do static router addressing. And we use a route-p add statement on router A to teach it about those other networks and how to connect to those other networks. So let's walk through how this works. If we have a node, let's say at 192.168.10.25, and it wants to send a frame to a node at, let's say, 1.2.168.13.55, we have to teach router A that if you want to get to that 13 network, you have to send the frame out your 192.168.11.1 interface to the gateway of 192.168.11.2 interface on router B so that it can then forward your frame onto 192.168.13.0 network. And that is the process we have to go through for the 13, 14, 16, 17, 18, 19, 20, and 21 subnets. So we would have a series of route-p add statements. By the way, the -p says make this route persistent. In other words, store it in memory. Even if the router is rebooted, bring this route back. Remember this route even if the router gets shut down. When it powers up again, remember this route. I don't want to have to type this in a second time. So the statement is route-p add, the destination network address, the mask, and the subnet mask, and this is in dotted decimal form. And then what is the gateway, the interface on the adjacent router that you want to send this frame to in order to connect to that remote network? And that last statement is metric. Consider that to be the number of hops from this router to that destination network. Each router is considered a hop. Now, this metric function also allows me to assign a cost to the route. As I maybe artificially inflate the metric, I'm saying this is not a preferred route. The routers will always send the packet through the route that has the lowest possible metric and will only roll to a higher metric path if that lower metric path is not available. So let's walk through the way this works. If I'm going from 192.168.10.25 to 192.168.13.55, I need to teach my router the following route. Route-p add 192.168.13.0, that's the destination network. The word mask and then the subnet mask for that network address is 225.225.225.0. That, by the way, is a /24 mask. And then I have to tell router A what is the interface on the adjacent router that is your path to that 13.0 network. Well, in this case, router A has to send the frame to 192.168.11.2 on router B because router B is attached locally to that 13.0 network. And I'll also tell router A that it is one hop to that 13.0 network. Now again, if I wanted to, I could steer the traffic down through C over to D and back up to B, but then I'd have to say a metric of 4 for this particular route that I just typed in. And now the 3-hop route down to C, down to D, and then up to B, that would be 3 hops. So the cheaper path is that CDB path. However, if that path gets broken or interrupted some way that I can't get through on that path, I'll roll to the metric 4 path straight from A to B rather than through that longer loop. Now, why would I do that? Suppose that 192.168.11.0 segment is a slow dial-up, or it's heavily trafficked, and I don't want to put any more traffic on it. So I can steer the traffic around that 11.0 network by adjusting the metric for the route mapping. So as you can see, we've added mappings for the 14.0 network and the 16.0 network. All this is done on router A. I'd have to go to B and C and D to teach those routers about the networks that are not local to them. As we look at router B, he's local to 11, 13, 14, and 16. But he doesn't know about 10, 12, 15, etc. So we'd have to go do a route-p add statement on router B for each of the networks that he does not have network interfaces attached to locally. Now, continuing on, what we just did was static routing. We can configure our routers so that they communicate autonomously amongst themselves and share this route table information amongst themselves. What a great idea. So now I don't have to go do that route-p add statement 63 times on 4 different routers. I can program these routers to use the same dynamic routing protocol, and I configure the protocol on each of these routers, and now they will communicate amongst themselves. There are primarily 2 different families of algorithms that dynamic routing protocols utilize. They either use a distance vector algorithm. Typically, this is only used for small networks, like up to maybe 15 nodes, 15 routers. And the larger of the 2 is called link state algorithms. This is used for medium and large networks. This is what the internet uses to communicate the route tables amongst the many, many, many routers on that very large public internet network. And you'll see a reference of a handful of the different routing protocols. RIP, that's the Router Information Protocol, RIP v2. Down below we have the link state algorithm is Open Shortest Path First protocol. Now again, that's the one that gets all the business on the internet. And again, the routers only know what they can figure out on their own through the dynamic routing protocols or what an administrator types in statically. And there is a potential that a router could establish a loop called a routing loop, where a packet hits a series of routers and actually never makes it out of the loop. In other words, it just continues endlessly until the router is discarded due to its old age. So there are several techniques that are used on routers to avoid this routing loop problem. And one is called a poison reverse, one is called a split horizon, and another uses something called hold down timers to avoid these routing loops. We'll take a quick break here and we'll pick up where we left off shortly. In this lesson, we're going to be discussing firewalls. Firewalls are network infrastructure systems that generally establish the boundary between different areas of the network that have different levels of trust. In other words, on my intranet, I have a high level of trust for all the nodes that are there because these are my employees, and these people have to come through the security control at the front where the security guard is. They have to show their badge. They have to go to their cubicle. Their fellow workers would recognize who they are, et cetera, et cetera. So I've got all these physical controls in place. And the users in this computing environment are relatively trusted. However, our network attaches to the branch office. Well, we don't know those people quite so well as we know the people in our office. For all we know, that branch office has been compromised, and there might be some user in that branch office that isn't authorized to be using the computers. So what we do to defend ourselves from these lesser trusted computers and nodes and users is we separate our intranet from that extranet with a boundary, a security device called a firewall. So the firewall is typically a routing type of a device. It's not exactly a router, but the original firewall was a router. It had an application added to it that did filtering. And so you can assign an access control list to the firewall that says disallow this type of traffic. And that could be based on its IP address. It could be based on port numbers. It could be based on protocol. And then some. We'll talk more about these as we look at the chronology of firewalls. Now, this device that we're talking about is typically a piece of hardware, a dedicated appliance. It can be an application on a computer, but typically a firewall is sophisticated enough. I'd rather buy a dedicated appliance that does nothing but firewall functions. And if I have a firewall on a computer, it's called a personal firewall, and it's just to protect one node, that one host. So that's a different type of firewall altogether. We'll talk about them in a few minutes. This is an appliance that typically will have multiple network interfaces, typically at least 2 and sometimes 3 or 4, depending on the number of demilitarized zones or screened subnets that we might want in our networking infrastructure. So we call a device with multiple network interface cards a multi-homed system. In other words, it has a home on this segment and it also has a home on that segment. And it establishes a connection point between those two segments, but it is a security device who is programmed to do filtering. It is also a hardened, called bastion host system, which means from one side, it's very difficult to penetrate. So it has a hard, crunchy outside that points out towards the public side, the less trusted side. But then on the inside, it might be a little softer and chewier because this is the trusted environment on the inside. So the firewall will typically have a public interface that is the hardened interface that has a default deny all rule built into it. And then it has a more gentle interface, the private interface, that points towards the trusted networking environment. So again, the firewall is used to establish security zones between networks of differing trust levels. And as you can see, we're going to quickly review 5 generations, the evolution, if you will, of firewalls and firewall technology. So let's move forward here. The first generation firewall was called a packet filtering firewall. Now, these are still around. We still use these on a regular basis. Basically, the packet filtering firewall is a layer 3 router that also has an application on top of it that allows me to add an access control list that can filter traffic out that I don't want. So based on IP address, based on port number, and based on protocol and direction, I can establish this packet filtering firewall. I'll build these rules in what's called the ACL, the access control list, and I can allow traffic that I think is good, and I can have the firewall drop all the traffic or block or deny all the traffic that I think is bad. Now, the problem with the packet filtering firewall is it was just a little bit dumb. It was fast and it was strong. It was hardened, so the bad guys couldn't break into it very easily. But the problem is it's only got a go, no-go capability. It's only red light or green light, and there's not much in the middle. So because we have to use the range of port numbers, if you recall, we have server-side port numbers that are the destinations of services that I'm requesting. And then we have the client-side port numbers that are pulled out of the ephemeral port number range that would range from 49,152 to 65,535. That client-side port number range had to be open 100% of the time. So there's a huge hole in your firewall. Imagine you build a fortress, but you leave a 200-foot gap in the wall. So you got 3 sides that are all wall and one side is missing. That's not a very strong fortress. So while it did do some blocking of some port numbers, there were so many port numbers we had to leave open because of the way the client-side port number is randomly selected from the ephemeral port number range. They weren't great when it came to overall security. They were better than nothing. They were our first generation of firewall, but they still had some problems. Again, because this was built on a router, this was a layer 3 network device. It made its decisions primarily based on IP address. It understood a little bit about MAC addresses, so it could do some stuff with MAC addresses, again, depending on implementation. And it understood only the port number. It didn't understand what the port number meant, but we could say anything to port 25 green light, anything to port 443 red light. And so while it could see a number and a go, no go port number, which is layer 4 functionality, it didn't understand what that number actually meant. It was just red light or green light on that port number. So it didn't really understand layer 4 protocols. That's why this guy still lives at layer 3. packet filtering firewall also didn't have any way to correlate series of packets, so it couldn't understand a flood type of attack. It couldn't understand a fragmented attack. So payloads that were malicious in nature would still sneak through this firewall because he had no way to put these pieces together and actually look at the picture and figure out, ooh, this isn't good. Stop this stuff. Basically, he was real basic. He could look at one packet at a time and give it a red light or give it a green light. Because this was a filtering device, it created what we called a screened subnet. And anything behind the firewall on the private side was a screened host. Anything on the other side, of course, that's the less trusted public area. And I don't care about what happens out there. That's not my turf. Those are the guys I'm defending myself from. Now, in the diagram down below, what we see is a packet filtering firewall placed external to your external firewall. So this did some initial filtering, and this is where we still might use this device, outside the external firewall to knock down a lot of the junk that I don't anticipate wanting to receive in my corporate environment. So I'll use this relatively cheap, relatively fast, relatively strong, but also relatively dumb packet filtering firewall to knock down a lot of the garbage that the public internet is throwing at my external firewall. That allows him to operate a little more efficiently only on the traffic I might consider receiving. So in this case, that external firewall, the EFW, is a screened host being protected by the firewall to the left of him, the packet filtering firewall. We're going to take a quick break here and we'll pick up on Generation 2 firewalls. We're picking up on firewalls relative to network infrastructure. And we're looking at the Generation 2 proxy firewall. Now, the proxy firewall had two different levels of capability depending on what you were willing to pay for. We had a circuit level proxy firewall and an application layer proxy firewall. Let's start with the circuit level firewall first. We'll describe the basic functionality of that guy, and then we'll talk about the increased capabilities and some of the downsides associated with the application layer firewall. So the second generation firewall had the goal of disconnecting the client computers on the trusted private network from the untrusted computers on the less trusted public network. When a client on the private side wanted to access a web server that was out on the public internet, the client literally transmitted his request to the proxy firewall, as if the proxy firewall represented the entire internet. So there would be a session established between the client computer and the proxy firewall, the firewall that you built, that you installed, that is part of your security network infrastructure. The proxy firewall, assuming the request was allowed due to the access control list, we might be filtering on a particular component here that the guy's asking for. But let's assume that the request is actually authorized and allowed. The external firewall, in this case, the proxy firewall, would then presume the role of the client on the public network and make the same request of the web server out on the public internet as if the proxy firewall is the client making this request. So as you can see, it actually broke the connection between the true client inside on the private network on the corporate LAN and the untrusted server on the public internet. Now, that web server out there on the public internet would assume the proxy firewall was the real legitimate client requesting information, and it would transmit its data back to that proxy firewall. The proxy firewall might have some rules, once again, that it might filter content on, but let's suppose that in this case, the proxy firewall says, yeah, the content looks good, I don't have any rules that should block this. So now the proxy firewall would act as the web server in this relationship and transmit the data down to the client on the trusted corporate LAN. So the client never actually communicated directly with the web server, and the web server never actually communicated with the client on the private LAN. The proxy firewall acted as the intermediary and broke the connection between those two nodes. Now, the circuit level proxy could have authentication capabilities. In other words, I could write a rule that said Bobo is not allowed to use the internet from 8 a.m. until 12 p.m. And if this particular request came from Bobo and was going to the public internet, I could now first authenticate Bobo, be sure I know who it is, because I've got rules now that say this guy can go and that guy can't go. And I'd authenticate who Bobo is, and then I would look for any rules relative to Bobo. And if the request came between 8 and 12, which is a deny period, I would simply reject this request, and Bobo would get a web page that said unable to connect to server or something along these lines. So we can use authentication now, the computer's name as the source of filtering. We also then could add to that the source IP address, destination IP address, source port number, destination port number, the protocol used. We can even filter based on domain name. Suppose the client is trying to get to sportsillustrated.com, and I don't want him watching a baseball game on Tuesday afternoon. I want him doing his work. So I might deny all requests to sportsillustrated.com. Oh, except for the senior management team. They can do anything, especially since they have some impact on my salary. So let's give them whatever they want. We'll block it only for the general users, but the senior management team, they can get to wherever they want to go. And I can turn on these filters, these ACLs, access controls, and identify who and what and when. So I have a great deal of control over connectivity out through this firewall. In addition, there are many known bad websites, web servers, destinations out there on the public internet. They have a well-established reputation. These guys are going to send you malicious software, viruses. They're going to try to steal your private information, etc., etc. So this blacklist, or these blacklists, because there are many sources of these, are published on a regular basis. And so what you can do is configure the blacklist on your proxy firewall. You can even configure your proxy firewall to reach out on a daily basis, download today's blacklist, and now anything on that list, any destination on that list, you're going to automatically deny. So we have this whitelist and blacklist capability. We could turn on a deny all public addresses and names other than those 17 that are on my whitelist. My clients are only ever going to need to go to these 17 places, put them on a whitelist, and then deny everything except those on the whitelist. I can build a whitelist or a blacklist and use this for filtering. Now, because we base the biggest part of our filtering on the IP address and a port number, these two pieces of information collectively form something called a socket. If you recall from earlier lessons, an IP address : port number is a socket. And if I want to consider the bidirectional, the full socket, I would consider the source IP and port and the destination IP and port, and that would be a true bidirectional socket. Well, since the very first circuit level proxy firewalls use primarily this IP address and port number as the filtering tool, they were referred to as SOCKS proxy, SOCKS coming from sockets. And in order for your client computers to use the SOCKS proxy, they had to be configured so that they treated your proxy firewall as the entire public internet. They sent their request to your proxy firewall, who pretended to be the entire internet. That proxy firewall would then filter or analyze that request, and if everything was allowed, that proxy firewall would go to the public interface on the firewall and act as the client. On behalf of the true client, he would then reach out to the public servers and pull that content down. Now, as we move towards the application layer proxy firewall, this guy added layer 7 functionality to the process and could actually reconstruct content that was pulled back down from the public servers and then run analysis, whatever type of analysis was configured and capable of that particular firewall based on implementation. We might do content analysis. And if we found it had to do with gambling or sports or pornography or something else that was undesirable on the corporate network, we could simply deny that content based on the rules for content filtering, based on what that content actually contained. Now, as you can imagine, this reassembly of all the content and then analysis of all that content and then comparing that analysis to your rule base takes a little bit of time. So these application layer firewalls, proxy firewalls, called an application layer gateway, provided deep packet inspection, but it took time. It was slow. And because it was so painfully slow, very often these firewalls would add a caching component to the firewall. So it would be a caching server as well. Now, if the client wanted to go to, let's say, google.com, the proxy firewall would have been there 63 times already today, and he would simply feed the client back the web page that he had already downloaded, analyzed, and then cached. Once it's been blessed, he'd feed it right to him from his cache. So hits from the cache are very fast because he didn't have to reach out and go get a new copy and go analyze it, and et cetera, et cetera. So the application layer proxy firewall, also called an application layer gateway, could do all the things that the circuit level proxy did, including authentication, computer name, source and destination, filtering, IP, port number, direction, domain name, whitelist, blacklist, now content filtering and caching. All these features were available on the application layer gateway. Now, if we were going to reassemble web content, I would have to install the HTTP proxy application. If I needed to reassemble and content filter FTP traffic, I'd have to install the FTP proxy application. So in order to reassemble the content to do the content filtering, my proxy firewall would have to have that application proxy installed on the firewall. If you didn't have that protocol installed on the firewall, that proxy service installed on the firewall, you couldn't proxy that particular protocol. It had those limitations. We will knock off here on the Generation 2 proxy firewall. That's it for now, and we'll come back and talk about more firewalls in a few minutes. We're picking up with the Generation 3 stateful firewall. Now, this was the third generation firewall. We've been through the packet filtering firewall, the proxy firewall. Now we're going to add to it the capability of something called the stateful firewall. This guy added a tremendous amount of capability to the firewall functionality. Remember, the firewall is a security boundary between two collections of segments that have different levels of trust. So this is your security boundary. You have a public side that is untrusted, a private side that is more trusted. And what this guy did is he said basically that everything inbound from the public side is by default denied. In other words, nothing is allowed through the firewall. Well, why not just disconnect the cable then? Well, here's the exception. The only way the stateful firewall would allow a packet through from the public side to the private side is as a client on the trusted inside, the private side, made a request outbound, the stateful firewall would document that request in a state table. It would record the source computer, the destination IP address, the protocol used, the port numbers used, and only if the inbound packet matched an outbound request. In other words, if I didn't request it, I'm not letting it through. Only if the firewall found a mapping on the state table where we actually requested that packet, that's the only time the stateful firewall would open up that hole dynamically, let the packet through, and then close the hole right behind that packet that is allowed. So this added a great deal of functionality to the firewall family. As you recall, the packet filtering firewall simply hardwired port numbers open or closed, and it was either red light or green light 24/7, and there were no conditions. Here, finally, I can say deny all inbound traffic to the client-side ephemeral port number range of 49,152 to 65,535. Deny all that traffic unless that inbound traffic is the response to a request we made from the inside. So this now, collectively, the packet filtering firewall, the proxy firewall, and the stateful firewall, when you add that functionality of those three technologies together on the same firewall, now finally you have a very strong, very secure, very functional security device. So it was only after we got to Generation 3 that we really had a pretty good handle on how a firewall should operate. And by coincidence, as I describe putting these together, what we're going to learn is the Generation 4 firewall is the combination of the packet filtering firewall plus the stateful firewall. So the fourth generation is let's put these functionalities together. And we call this a dynamic packet filtering firewall. And that dynamic part is relative to the stateful firewall's dynamic opening and closing of ports only if it's a stateful response to a request we already made. So here we're going to see that I can now support internal services by hardwiring, let's say, port 80 and 443 open inbound, and I map them directly to my web server. And I'll also open port 25 inbound, and I'll map that port number to my email server, and then I'll deny everything else using the packet filtering functionality. In other words, anything that's not something I've requested and isn't going to my web server or my email server, the answer is I'm going to reject it. Oh, wait a second. What about when my clients make a request of something outside? Well, that's where the stateful component of this dynamic packet filtering firewall comes into play. Remember, the stateful firewall says all inbound ports are closed unless I have already recorded on my state table a request that came from the inside outbound requesting that traffic, and only if it's a stateful response to something we've requested that I'm going to allow. However, if it's an unsolicited inbound packet, then I'm going to reject it. Unless it goes to port 80, 443, or 25, those the packet filtering firewall always allow and will steer to either the web server or the email server. And so you see this fourth generation dynamic packet filtering firewall is the bomb when it comes to really what do we need for firewalls. So most of our firewalls today have this dynamic packet filtering firewall capability, and if it's desired, many of them also have the proxy functionality as well at either circuit level or application level. We'll move forward now and look at the fifth generation firewall. Now, this firewall came out in the mid to late 80s, maybe early 90s. There were some of these around. Now, the deal is this. Each of these firewall devices are actually sort of like a computer. They have a CPU, a processor, and they also have a program, sort of an operating system that describes how this device is to operate. Well, the operating system is typically broken into two different modes of operation. The more trusted kernel mode, which generally are functions that support the operation of the device. And then we have the less trusted user mode, and those are the functions that something external is trying to request from us, like some other application or process or other thing. Now, the firewalls historically had been operating in the user mode, the less trusted area, because we were trying to protect the functionality of the device itself. And we isolate those functions down in the kernel mode. Now, they figured that the firewall would benefit by adding the firewall functionality down inside the kernel of the operating system. In other words, make this device inherently a firewall at kernel level, and then I don't have to go through this boundary of user mode, kernel mode, and making requests. When the kernel makes up his mind to do something, he's allowed to just do it. The problem, though, is what is this firewall device actually doing? He is isolating a trusted environment from a less trusted environment. And if this device has to handle information flow from this less trusted environment and also handle it at the heart and soul of the kernel, that malicious software that might be coming from that public untrusted network is already in the heart of the kernel, the heart of the operating system, the heart of the device. In other words, it put that dangerous stuff way too close to the heart and soul of your firewall. And while they made these kernel proxy firewalls for about, maybe 5 to 10 years, it soon became recognized that that's just not a bright thing to do. We want to keep that dangerous stuff on the other side of the fence and only allow interaction through a security filter, that boundary between the user mode and the kernel mode of the operating system for this device. So we don't really see a true kernel proxy firewall in implementation today. Some of the components of the firewall were kept down in the kernel mode, but a rare few, and all the interaction with all the hazardous stuff from the public untrusted network, that's all handled in user mode. So the true kernel proxy firewall doesn't exactly function or exist today. It's more of a historic review of a technology that has since been pretty well discarded. Well, this pretty much completes the analysis of the 5 generations of the firewalls. We're going to look a little bit more about firewall architecture coming up. In this lesson, we're going to be looking at a handful of rules that are commonly implemented on our firewalls. Remember, the firewall is a security device that separates segments of differing levels of trust. I have a private side that is trusted and a public side that is less trusted. Almost always there is a default deny rule built into the firewall. In many cases, it's a rule that can't be deleted because it is one of those core fundamentals. If you were to accidentally delete your default deny rule, your firewall isn't a firewall anymore. It's nothing more than a fancy router. An overblown router is what it is. So the default deny rule says drop everything in both directions unless there's a rule that specifically allows that type of traffic. That's our default deny unless there's an explicit allow rule. Generally, when you're building this list of rules in what we call the access control list, the ACL, you want to keep it as simple as possible. Keep your rules very straightforward, very direct, and if the firewall allows for some sort of built-in documentation, why is this rule here? What is it supporting? Why did we need it? Is it temporary? Is it permanent? Etc., etc. You want to be able to document each and every rule, what it's about, because 3 years from now, some guy named Bobo is going to be working on this firewall that you set up. And 3 years from now, he's not going to know what the heck that rule is doing or why it's there. But if you documented that it's there to support the application web server, then he knows what it is and he knows it has to stay. So document your rules. Always enable logging, and those logs should be sent off to a remote logging repository server. Today, we have many different laws and regulations like PCI compliance and Sarbanes-Oxley and HIPAA and Gramm-Leach-Bliley Act that require certain security components be in place, and they almost all include you have to spin your logs off to a dedicated log repository through guaranteed delivery, secure transmission, hardened bastion host log repository, etc. You need that logging enabled, and you probably want to spin it off to some remote system to store those logs, and perhaps even spin them off through a security information and event management system that will do real-time artificial intelligence to correlate very complex, structured, and slow and low type advanced persistent threat attacks. So we need to enable that logging, spin it off to some place for secure archival, and analyze it. Logging is great if you look at it. If you don't look at it, you're wasting hard drive space. Build yourself a whitelist if your environment supports such a thing. These are the always allow traffic to these destinations because these are the 17 places we always need to go. So don't block any traffic to these locations. It can be nothing but the whitelist where we deny all except the whitelist, or it can be always allow to this whitelist. There's also a blacklist that is a possibility for most firewalls, and this is a list of destinations that we are never allowed to communicate with because they are perhaps known bad guys. It might be my competition. It might be a site that pumps down malicious software and viruses. So the blacklist we can very often download from many different locations on the public internet. A lot of times our firewall vendor will provide us a regularly updated blacklist that we can download and incorporate into our firewall. Along with this blacklist is an area of the internet called the Internet Dark Address Space. So this would be another collection of locations on the internet that we don't ever want our clients to connect to. Now, this dark address space is called that because it hasn't been officially allocated by the regional internet registries. In other words, it's an IP address that isn't supposed to be functioning on the internet. But what the bad guys do is they figure out what this dark space is, and if they can break into one or two routers on the internet, they can configure the routing system so that these nodes, in spite of the fact the address space hasn't been allocated, these nodes can still be routed to. And so the bad guys will set up their malicious servers in this dark address space on the internet, and we never would want our clients to go there. So along with our blacklist, we might kill off any traffic outbound to this internet dark address space. Another term is this BOGON, and this again is unallocated public IP address space, and again also very often where the bad guys live and breathe and try to draw us to. So the internet dark space and the BOGON space, these are similar in some regard in that it's typically unallocated address space, two different names and perhaps some slight different interpretations on them, but generally we're talking about the same thing. Now, these next two filters are typical, should be on every external firewall, the one that is connected to the public internet and connects to your corporate private address space, your private networks. The ingress filter says, because private address spaces in IP are not allowed to operate on the public internet, if an inbound packet ever arrives with either a source or destination IP address that's out of that private IP address space, deny this traffic because it's almost certainly malicious. It probably is an attack on the source IP address that is a private IP address. Somebody on the outside public internet is trying to attack one of my computers on the internal private address space. We don't want this coming through my external firewall, deny it. That's called an ingress filter because it's inbound. Now, similarly, there should be an egress filter. Egress filter is relative to outbound traffic. Egress implies outbound. Now, on my private intranet, this should be running nothing but the private IP address space. That's a 10 dot something, a 172.16 dot something, a 192.168 dot something. Those are the three private address spaces that should be used behind that external firewall. Now, if I have an outbound packet that has a source IP address that is public, that shouldn't happen because all the nodes on the inside should be using nothing but private IP address space. If a node on the inside sends a packet outbound where the source IP address is from the public address space, this is also probably an attack. And more horrifying is an indication that the node that actually sent this has been compromised, and a bad guy who is now in charge of this computer, called the handler, is actually using this computer on my network to attack some other computer on the public internet. So an egress filter denies outbound packets that has a source IP address in the public address space. These should always be denied. And then, of course, there are a collection of already understood vulnerable protocols, and they're vulnerable for many different reasons. Perhaps the username and password are sent in clear text. Perhaps it's a protocol that's used to scan the network, like SNMP, that implements source routing. It could be another protocol that's used during different types of attacks, etc. Well, any of these protocols that I know are used commonly as attack vectors because the protocol has vulnerabilities, I should deny that type of traffic, especially inbound. And if I care to, I should probably also deny it outbound, but I want to be alerted to it when it goes outbound, because that says one of my guys inside is doing something they shouldn't. So these are the collection of firewall rules that should be implemented on almost every external firewall, the boundary between the public internet and your private segments. We'll quit here for now, and we'll pick up with more firewall information in the upcoming lessons. Let's continue with our review of firewalls, and in this particular lesson, we're going to be looking at the architecture. Where should we plug firewalls into our corporate networking environment? So let's look at this diagram now, and let's identify where these firewalls are and why they are here. Let's look in the upper left-hand corner where we see the websites and the public internet. This, of course, is the hostile, untrusted public internet. This is the major source of all of the malware and the attacks that our corporate network environment might be subjected to. The bad stuff we want to stop from coming into our network. As we follow that line to the right, we see that very first firewall there, that little brick wall, and that is my external firewall. Now that's the guy that takes the most abuse. So very often in front of that guy, I'll install a relatively inexpensive router that has an access control list on it, a generation 1 packet filtering firewall to act as a screening router that drops all of the type of traffic that I would never want to let into my DMZ or my private network. So I'll put a very inexpensive, cheap packet filtering firewall to the left of that first firewall there, and that will knock down a bunch of the garbage that my external firewall would otherwise have to contend with, just wasting his time and resources. Let's put him to good use on only filtering the type of traffic that I might consider tolerating on my DMZ or my private network. So that external firewall is one of my key guys right there. He also is typically running a protocol that we'll be discussing in later sections in this series of lessons called Network Address Translation, that is also closely associated with port address translation. So NAT and PAT are typically always functional on that external firewall. We see to the right of that external firewall a second firewall, and the region between those two firewalls is often referred to as the perimeter network or the demilitarized zone, the DMZ. Now, the DMZ is named that because this is a pretty hazardous area. This is an area where we have public-facing services that must access or be accessed by the public internet. That's where all the bad guys are. These guys get taken pot shots at all day, every day. The bad guys are hammered on these boxes trying to break into them all day, every day. So this DMZ is fraught with attacks and bad guys and differing levels of perhaps even compromise. Again, we consider this still be a very hostile area, yet this is an area in my private network space. These are my machines, my servers, my switches and routers that connect these public services together to the firewalls. But again, these are areas where I don't put anything on those servers that I don't want to give away to the bad guys. Don't put anything valuable on these publicly exposed servers. Now, what type of services are these? These are web servers, email servers, FTP servers, DNS servers for my public systems, and things along those lines. So that's the type of stuff that must live there in that DMZ, and these are the guys that are going to get hammered on by the bad guys all day, every day. Now that internal firewall, the second firewall there, that guy is still a very critical firewall for me. That guy's going to have a lot of rules that's going to filter anything from that public space away from my private local area network, my intranet. And so this is where all my trusted computers and computing environment exists, all my resources, all my clients. That's where they all exist. Now, very often, I'll have my users that travel, and they'll connect back to the home office through the internet, through my DMZ, and they'll need to attach to resources on that private LAN, that intranet. Well, I don't want them pulling my sensitive data over the internet in clear text. I'll want them to encrypt all that information, and to do that, I'll have them build a secure channel, a virtual private network. So that one of the first devices we see behind that internal firewall is a VPN concentrator. So anybody who's out in the public internet who needs to access something on the private network will come through the DMZ and attach directly to the VPN concentrator, authenticate securely, establish a secure channel, a VPN, and now they can communicate with these internal private resources. The VPN concentrator will encrypt it before it allows it to flow out to the client, and then it gets decrypted on the client computer, that trusted, authorized client out there on the internet. Next, we see the LAN, and this is our collection of routine resources. These are file servers, application servers, the different types of print services, things that we need on our corporate LAN, our secretaries, our work staff. Other departments will utilize the resources on this main part of our corporate network. However, if any of the information they're accessing is considered more sensitive than routine information on our private networks, like accounting information and our research and development, our intellectual property, the real value for many companies, we would consider those segments, those collections of servers and client computers are touching more sensitive data, more valuable data, and I want to isolate those segments from the rest of the corporate LAN. Remember, that firewall is a boundary between a segment that has a high level of trust, like the accountants in the accounting department, from a lower level of trust, well, the secretaries in the secretarial pool, for example. And so I'll put this firewall in between the accounting segment and the rest of the corporate network to allow another layer of filtering and isolation between the highly sensitive data and processes occurring on that accounting segment and the lesser level of sensitivity and processing of data on the corporate LAN. And similarly, a firewall between the corporate LAN and the research and development department, because again, that's where a lot of our intellectual property is. That's where a lot of the value of the enterprise exists, in this R&D area of computing. Now, as we look down towards the bottom and over towards the left a little bit, you'll notice 2 wireless access points as an example. And if you follow that line back towards the corporate LAN, you'll notice there's a firewall there that isolates the wireless access points from the corporate LAN. Well, you might say, well, those access points, those are inside my building, so those should be trusted. Well, slow down there a little bit. The point is, a bad guy in the building across the street could be attached to your wireless access point. Therefore, always treat your wireless traffic as hostile, because you can't see who it is that's attached to that access point. He doesn't have to come through your front door. He can be in the building adjacent. He can be on the street, in the parking lot, around the corner. And even a bad guy with a good antenna can be 10 miles away and still attached to your wireless access point. So you don't know who that guy is, who is perhaps trying to authenticate and associate to your access points. Always treat that traffic as hostile. So this diagram is a pretty cool but generic map of a good way to implement your firewalls. They are security boundary devices between network segments of higher trust from isolating them from network segments of lower trust. This map here is sort of the architectural overview of the way you want to think of placing your firewalls. We'll quit for now and we'll move forward with the next section of this lesson. Next, we're going to look at some network services. Let's start with Dynamic Host Configuration Protocol, DHCP. This service dynamically assigns IP addresses to DHCP client nodes on the network. Typically, you will statically assign IP addresses to your servers and infrastructure systems, and it's typically the client systems that are dynamically configured using DHCP. The next service we're going to look at is a name resolution service that maps the fully qualified domain name of the various nodes on the network to the IP address. So this provides name resolution services. Users are familiar with the friendly names of the nodes on the network, like webserver1.boboville.com, but DNS system provides the IP address for that named system so that the IP network stack can accurately transmit the queries and responses back and forth to the appropriate systems. Next service down is X.500 or directory services. Now, this is the network service that provides us a security structure. Objects within the Active Directory or within the directory services database are typically trusted objects, and objects outside this directory services database are untrusted. So this is a way that we can authenticate and authorize user access to resources on the corporate environment. This is typically a corporate level or an enterprise level service. The next service we see here on the list is for email distribution and storage. We'll start with the Simple Message Transfer Protocol, SMTP. SMTP protocol transmits email from client computers to the email servers and from email server to email server for email distribution. However, SMTP is not used for client retrieval of email. So SMTP is from client to server and from server to server email transmissions. For a client to download their email, they will typically use either POP3 or IMAP4. That's the Post Office Protocol version 3 or Internet Message Access Protocol, IMAP4. Now, these are client retrieval protocols for email, and this typically requires an email application, something like Microsoft's Outlook application. It's not uncommon that the email server will also provide a web-based access, but this uses a browser. So this is typically done over port 80 or the SSL equivalent 443 for the email retrieval if that retrieval is done over HTTP or HTTPS. Moving forward, we'll look at some other networking services such as file sharing services. Now, on the enterprise network, we will typically provide repositories, server-side repositories for all of the enterprise's data files. We typically don't want these data files left on client workstations because very often these client workstations may get damaged. If they're laptops, they're traveling around, they may get lost or stolen. Typically, in the enterprise, we want central repositories for these data files so that we can easily facilitate and help to ensure successful backups of these in case of disaster recovery requirements. So we have LAN-based file sharing services. We also have internet-based file sharing services. Essentially, HTTP, the web protocol, hypertext transfer protocol, is for file sharing. It actually is a file distribution protocol. However, it builds into it on the client side a processing and presentation function as well. So it isn't just direct file sharing. A classic file sharing service for internet-based is the file transfer protocol, FTP. Now, this is one of the original internet-based protocols for bulk file transmissions. And more, we are moving towards cloud-based services for file sharing. In other words, we will have a cloud environment, perhaps private, perhaps public, if we want to lease space on someone else's infrastructure. But we will use web-based services now for our file repository and then later file retrieval, file access. So this is cloud-based services, a relatively new component in our file sharing services. We also have the need to print very often. So in an enterprise environment, we don't necessarily want to buy a printer for each cubicle, each user. So we very often will have a printer pool, and users will share a printer. So we'll need to provide a printer server and then share those printing services to users. We have application sharing services, and these are typically client-server-based applications, such as the email services that we referred to earlier in this lesson. And the client-based component would be perhaps Microsoft's Outlook or some other application along these lines. So this is a typical client-server application sharing service where the client requires or desires the use of a particular service, and he actually has an application that is configured and specifically tuned towards that server's services. Now, something that we'll find very often in the enterprise, maybe not so often at home, is remote access of the networking environment. And this requires network access services. So these are typically for remote access. Because the users that use remote access are not within the physical confines of the facility, we have heightened concerns about authenticating these people more strongly. Because they don't have to walk past our security guard with a badge, they don't sit down in a cubicle in our office where the coworkers would recognize a stranger versus recognize that this is the authorized user for this environment. We need to more strongly authenticate these remote access users. So we'll typically use what we call a AAA service for authentication, authorization, and accounting. Today, that third A, accounting, is more often auditing or accountability. Back in the early days, this literally was a cha-ching kind of accounting where we're going to bill somebody a nickel for every kilobyte they upload or download. So these AAA services start with the remote authentication dial-in user service, terminal access control, access controller services, and Diameter, the new generation of these AAA authentication services. We very often will have true dial-in services. Now, these would be using an analog modem over telephone lines. These were the original remote access servers, and it was truly dial-up using telephone lines. Now, that same service has evolved to include the virtual private network or VPN concentrator services. Wireless access points and controllers also will use these strong authentication services for remote access. And also, an ancillary or support service for these remote access services is network access control to substantiate and validate the security health of these computers, these remote nodes that are trying to access our corporate enterprise. So typically, we'll very often implement network access control to qualify the state of the security health of the remote accessing node. And if they aren't healthy enough, we remediate them to a specific LAN, isolate them on this LAN, and provide then services such as antivirus, patching for updates, things along these lines. So if there are any sort of security concerns, we let them remediate themselves once they get healthy enough that I can trust them on my corporate LAN. Perhaps then I will allow them to access resources after they've been strongly authenticated. And finally, a service that is commonly used on the enterprise network for strong authentication and security is certificate services based on X.509 digital certificates. So these are a handful of network services that help to support and substantiate the enterprise level computing environment. We'll take a break here and we'll pick up shortly. In this lesson, we're going to pick up with some more detailed analysis of some of these infrastructure components or services. Now, the first one we're going to look at is Dynamic Host Configuration Protocol, or DHCP. And again, this is used to dynamically assign IP address configuration details to DHCP client nodes on the enterprise network, typically enterprise network. This might also be used in the home as well, but the level we're talking about here, we're looking at an enterprise. Typically, your infrastructure systems like servers, routers, DNS, DHCP, these services will have a statically assigned IP address and other IP configuration details. This would be defined by the network administrators, and they would manually sit down at each of these systems and manually and statically configure these details. However, we might have, let's say, 100 servers. Well, those 100 servers might support 2,000 client computers. We don't want to have an administrator sit down at 2,000 different client computers and maintain these IP configurations on these systems. So what we'll do is we'll set up this infrastructure service called DHCP that will dynamically allocate IP address configuration details to these client machines. Now, as you see on the dialog on the right-hand side of this slide, this would be the IPv4 configuration dialog in a Windows computer. And as you can see, this particular system is configured to be dynamically assigned IP information, including IP address, the subnet mask, the default gateway. That gateway, by the way, is the router that is local on this node's particular segment. And we also would dynamically assign the name resolution servers IP addresses here on this same dialog. So we could use the lower radio button to statically input each of these parameters if this were perhaps an infrastructure system. However, if it's a DHCP client, we'll use the upper radio buttons that says obtain an IP address automatically and obtain DNS server address automatically. That says this is a DHCP client. Now, DHCP is a broadcast-based service. In other words, when a client node boots up and loads its network stack, including IP version 4, the system will check to see if there is statically assigned IP parameters, such as IP address, subnet mask, default gateway, DNS, perhaps some other details as well. And if it is not statically assigned, then this client, this IP stack, recognizes that it must acquire this IP configuration information from somewhere. So it sends out a discover frame, a DHCP discover broadcast, and says, hey, if there's a DHCP server out there, please, I need an IP address. Now, if there is a DHCP server that hears that broadcast, in other words, it's within the same broadcast domain as the client that transmitted the request, the discover, the DHCP server will submit a DHCP offer. That's from the server back to the client, and it says, hey, client, I'm a DHCP server, and here's an IP address. Now, because of fault tolerance, we very often will configure in the enterprise multiple DHCP servers that can hear each DHCP broadcast. Just in case one of the servers is down, the other server can provide the IP configuration. So very often, multiple responses or offers will be provided in response to the DHCP discover. Now, the first offer that the client receives, that client will request that particular offer from that DHCP server. Why? Because that server was the first one to provide the offer, therefore I'm getting better service from him than from anybody else that's providing offers. The client will submit a request broadcast back to the DHCP server, and that same DHCP server will now reply with a broadcasted acknowledgement, DHCP ACK, or acknowledge. So our 4 frames are discover from client to server, offer from server back to client, request client back to server, and acknowledge server back to client. So it's a 4 broadcast process to acquire an IP address on a DHCP client. As we said, your infrastructure systems are typically statically assigned, and historically, DHCP is the 3rd generation. First, we had reverse address resolution protocol. This was the very initial way that client computers could acquire an IP configuration set of parameters. That evolved into something called the boot protocol, or boot P, and then finally DHCP. Now, as these protocols evolved over time, more and more services were built into them, more and more capability was built into them. So DHCP is the current 3rd generation of the dynamic assignment of IP configuration details for the clients. Now, the DHCP is not authenticated. In other words, any computer, good guy or bad guy, that can connect to your IP segment could acquire IP information and communicate with the DHCP server. So the concern here is, because it's unauthenticated and anybody can access this DHCP server, that makes the DHCP server fairly vulnerable. So there are a handful of attacks that are available in the DHCP protocol. Now, the first one is that a bad guy can stand up a DHCP server if he can plug into your segment. In other words, anybody who has either physical access to your wired infrastructure or perhaps access in your wireless infrastructure could stand up a DHCP server and provide bad information to these clients. In other words, this is a denial of service attack in this particular case, because let's say the network is a 10.10.10.0/24 network. Well, the bad guy could set it up as 172.16.0.0/24 network, and the clients that use him for DHCP will not be able to connect to the enterprise. And again, remember, this is unauthenticated, it's all broadcast-based, and the client will request the offer from the first DHCP server that responds. He can't tell whether it's a good guy or a bad guy. So standing up a rogue DHCP server is one of the easiest attacks to accomplish. It's a way to implement a denial of service attack, or we might actually steer those clients towards the bad guy networking infrastructure in an attempt to try and steal sensitive information. So we're keeping the good guys away from the real legitimate services, and we might actually be able to steal sensitive information or perhaps inject malicious software into these client computers. Now, another attack on DHCP is a client computer can request 100 or 1,000 or 10,000 IP addresses. All he has to do is have the client node acquire an IP address for a certain period of time, and then that node would submit a new request for a new IP address using a different MAC address, and then make a request for a new IP address using a different MAC address. The DHCP server can't tell that these are all the same computer. He thinks he's just a very busy guy, that there are a lot of client nodes in need of IP addresses. And before too long, the bad guy who's acquiring all these IP addresses unnecessarily will deplete the available pool of IP addresses. Now, Legitimate clients cannot acquire an IP address. Why? Because the bad guy has used them all up. So there aren't any more available IP addresses for legitimate clients. This is another denial of service attack. Now, in other lessons, we described the layer 2 device called the switch. And the switch today has replaced all the hubs and typically connect directly to each client node. Because we have a little bit of intelligence on this device, we now can apply an application to that device that can filter, and using an administrative console on many of these new enterprise level switches, we can implement something called DHCP snooping. And snooping would allow us to configure the one port on the switch that the DHCP server lives on. And if any other port on that switch provides a DHCP offer, the switch will simply discard that frame and will not forward it to anybody. So DHCP snooping will isolate the only authorized DHCP server to defend against the rogue DHCP server attack. In addition, the switch can also monitor each port, and if it sees multiple MAC addresses on a single port, it can be configured to deny additional DHCP requests. This will help us defend against the depletion of the available IP addresses on the DHCP server. So these are a handful of the attacks on DHCP and the new security that we can now add onto switches called DHCP snooping to help defend against these attacks on this vulnerable, unauthenticated protocol DHCP. We'll knock off here for a few minutes and we will pick up later with additional network services. Next, we're going to look at another networking infrastructure service called Domain Name System, or DNS. Now, as we've said before, DNS provides name resolution services. In other words, users are familiar with the friendly names of the infrastructure systems like webserver1.boboville.com or fileserver1.luluville.com, different names along these lines. These are called fully qualified domain names. However, in order to connect to these friendly named systems, the network stack must identify the IP address for that particular node. And that's where DNS comes in. DNS is basically a database that holds these mappings of these friendly names called fully qualified domain names, and it maps that fully qualified domain name to the IP address so that the network stack can actually use the network to transmit the frames back and forth. Now, the holder, the container, if you will, for these server names are called the DNS zone. And the namespace, like boboville.com, defines the zone name, and then the different local hosts, that would be like web server 1, file server 1, domain controller 1, these different local host names, then inside the boboville.com container, hold the mapping to the specific IP address. You can actually see this in the dialog box in the lower right-hand corner. We're looking at contoso.lan is the namespace, also called the DNS zone name is contoso.lan. That's on the left-hand side. It's highlighted in blue. And then inside that container are the actual mappings of the hosts, the actual server names, who are members of the contoso.lan namespace. And we see there's a DC1-2008R2. That's the local host name of a domain controller who is a member of the contoso.lan domain. And as you look to the right, you can see his IP address is mapped at 192.168.149.100. So there is that local host contoso.lan mapped to an IP address. That's a fully qualified domain name mapped to the IP address. That's what DNS does for us. And when a client needs to locate DC1-2008R2, that particular local host name, their client computer appends their domain name, contoso.lan, to that local host name, and then submits a query to port 53, the DNS server, and the DNS server searches his database in contoso.lan looking for the local host name that was requested, and will return the DNS response of the IP address that it has in its database, that it has mapped. So this is the name resolution process. Now, if a DNS server receives a query for a name he doesn't know, specifically a namespace he doesn't know, then that DNS server has the potential, if it's configured to do so, to ask an upstream DNS server. There are two different processes. These are called either forwarders, where we configure the server, if you don't know a name, go ask that DNS server, or the root hints. Now, the root hints are typically what's used when we get into the public namespace, out on the public internet. So internally, you'll very often use forwarders within your directory services environment because DNS is used for directory service support. And typically, you'll use forwarders internally and eventually forward out to a DNS server that has access to the root hints to support your client computers that are trying to browse the internet. And that's where we get our public namespaces that we would find out on the internet. When a DNS server forwards a query, either using the forwarders or the root hints, then if that server receives a response, he will cache that response typically for 60 minutes. This is referred to the time to live, TTL. It'll typically cache that response for 60 minutes so that it kind of memorizes that name to IP address mapping just in case somebody else requests that same information. And then it feeds that information, that mapping, back down to the client who requested that IP address mapping. Now, the client will also cache that information for the remainder of that TTL. As I had mentioned, DNS is a requirement of the X.500 directory services systems. Now, in implementation, directory services is most commonly implemented in Microsoft's Active Directory. The client computers that are members of an Active Directory domain must find a DNS server that has these service locator records, or SRV records, that are used to support directory services. So to support directory services, we must use DNS. The clients must be able to find that DNS server so that when they query for a domain controller to log into, if they can't get a hold of DNS, they can't log in, because that's the only way they know how to locate that domain controller is by looking for these SRV records for their namespace, like contoso.lan. Now, we've talked about internal DNS and external DNS. We need to provide internal DNS support for directory services support, and we need to provide external DNS, that's public DNS, for browsing of the internet. So your client computers need to be able to get to both systems, internal DNS and external DNS, private DNS and public DNS. However, we don't want to put our private DNS information out on the public DNS system because this is too clear a mapping for the bad guys. This maps out our entire infrastructure for the bad guys. So we don't want to make this internal IP address mapping and name mapping. We don't want to make this available to the public internet. So we will split our DNS and keep a private DNS for internal use and directory services support. And I never want that information to show up in the public DNS zone data. And so we'll use two different DNS systems to support these two types of services, one for internal directory services and one for external browsing of the internet name resolution services. Now, the original domain name system was referred to as the Berkeley Internet Name Daemon, or BIND. This was introduced in 1988 and is primarily used in Unix and Linux systems. Currently, BIND is in version 9, and Microsoft also implements their version of this domain name system and simply calls it DNS. We'll knock off here and we'll take a closer look at the DNS architecture in our next lesson. In this lesson, we're going to analyze more closely the architecture that we would set up as an example for the DNS system, the domain name system. And this architecture we're going to look at supports both the internal private DNS namespace, keeping it secure and private, and also provides support for the public name resolution services. Again, an example, there are many different ways to set this up, but this tends to support all of the required components. So let's start by looking at the lower left-hand side of this. And in this example, we're going to be using the example from Microsoft's Active Directory, the implementation of directory services. And we're going to do this because the Microsoft Active Directory is the single most commonly deployed directory services environment. So we're going to use that as this example. Lower left-hand corner, what we see are the domain clients. These are the users in the enterprise networking environment. And typically we'll take multiple DNS servers deployed in the environment so that we have fault tolerance. We'll take about, in this example, since we have 2 DNS servers, we're going to take about half of our domain clients and point them to one of those DNS servers. In this case, on the left-hand side, we start with domain controller 2 or dc2.boboville.lan. Now, that's the fully qualified domain name for that domain controller that is also a DNS server. So in the Microsoft environment, you want your domain controllers to typically be DNS servers as well. And I'll take about half of my clients and point them to DC2 as their preferred DNS server. And just in case that server is offline for maintenance or some network interruption, we also give them an alternate DNS server service to query, and that would be dc1.boboville.lan, a second domain controller for this Active Directory environment. And then on the right-hand side of those, we see the other half of the domain clients that use the preferred DNS server for DC1 with an alternate pointing to DC2. This is for load balancing and fault tolerance. Just in case one of those domain controllers is down, all the clients can still get name resolution services and still find directory service support for their internal directory services requirements. Now, this is our private namespace, boboville.lan, and all the client computers will need to access that boboville.lan namespace to get this directory services support. But what happens when those clients want to browse the internet? We have to provide this support. So what we do is we point these DNS servers, DC1 and DC2, to another DNS server, a separate system, and this particular system does not support the directory services. It doesn't contain or hold any of the mappings that are used internally to support this directory services environment. So we will forward any queries we don't know to this caching-only server. So this server does not have any records mapped in its database. The only records it will ever have are when it forwards a query outbound to the public internet and receives a response, it will cache that in memory for whatever the remaining time to live is, the TTL is for that record. So that's why we call it a caching-only server. We make this system not a domain member because we want to isolate this communications server, this DNS caching-only server, from Active Directory because that's too sensitive information, and this box will regularly be communicating directly with systems on the internet. And I don't want those systems on the internet to be able to perhaps attack this box and gain any more information. So I'm putting this guy as kind of an isolation boundary between my private namespace, boboville.lan, and the public namespace that we find out on the public internet off to the right in this particular diagram. When a client queries, let's say DC1 for www.goodstuff.com, the boboville.lan name server, DC1, doesn't know that namespace. It doesn't have a record stored locally for www.goodstuff.com. So DC1 will forward that query to the DNS caching-only server. So that caching-only server is now called a forwarder. That caching-only server also doesn't hold any records, so he's going to forward that query out now to the public internet. And typically what I like to do is forward to my ISP's DNS server. I want him to do the work and send back only the response. I don't want to get involved in a querying process, an iterative querying process that goes back and forth. So what I'll do is I'll forward my query out to my ISP's DNS. Now that ISP, that's my internet service provider. That's the guy who provides me my internet connection for my enterprise. And typically they'll provide this service as part of your monthly subscription for connectivity to the internet. So I'll let his server do the work for me. And so I'll forward this same query out to that ISP DNS server. Now that server will have his root hints enabled, and that means he's going to do the iterative query process out on the public internet to identify the actual IP address for the server named www.goodstuff.com, the query that came from that client back in this private environment. So he's going to run to the root server, submit a query. That root server will point him to the .com server. The DNS server from the ISP is going to now go query the .com server for www.goodstuff.com. That .com server will send him back the IP address of the name server that is authoritative for goodstuff.com. Now, the ISP's DNS server will go query goodstuff.com name server and should receive the response for the www.goodstuff.com mapping. That ISP DNS server will now cache that response and then forward the response over to the DNS caching only server for boboville.lan. That caching only server will forward that response down to the dc1.boboville.lan, and that DNS server will forward the response down to the client. Now the client can connect directly to that www.goodstuff.com web server out on the public internet using the IP routing system. So that's how the public queries are supported through the use of forwarders and root hints to get our public namespace resolved. The boboville.lan name servers also provide the internal support for directory services. Now, all that said, we have to recognize that we're here at boboville.lan, but we have a boboville.com public service or namespace that we want to provide web servers, email service, perhaps FTP services. And so we'll have some public services in the DMZ, the demilitarized zone between the two firewalls. And so we want the public to be able to come to our systems and browse our internet so they can buy our stuff off our website. We want to be able to have them send us emails, so we'll have a web server out there. So we need the public to be able to find our public services. And so what we'll have then is our public DNS service for boboville.com namespace. Notice the change in namespace now. Our public namespace is boboville.com versus our private namespace is boboville.lan. And so we'll now have a second zone for boboville.com that is stored in DNS and accessible by the users of the internet out in the public internet space, and they'll be able to query our DNS for boboville.com and resolve our www and our SMTP servers that are out there in that public namespace. Now, I would need that namespace to be very secure. So what I'll do is in my internal systems, dc1.boboville.lan and dc2.boboville.lan, I'll create a second namespace for boboville.com. And I will say that this is a non-dynamic DNS. In other words, it won't take dynamic registrations. And I will manually configure the mappings for www and for SMTP and for FTP and whatever other servers I want to put out there in that DMZ and provide public access. And what I'll do is I'll set this up as a primary DNS server for this boboville.com, my public namespace. And then the DNS servers out in the DMZ will be secondaries, which make them read-only so that the bad guys can't modify them easily. And now, anytime I make a change, I will configure my internal server on DC1 and DC2. I'll configure them so that anytime I make a change to the boboville.com namespace, it will automatically go update those secondary servers out in the public DNS DMZ that hold that same boboville.com namespace. Now, those two DNS servers up in the DMZ will only ever hold that one zone, boboville.com. They will never hold information for boboville.lan. Why? Because those guys are going to be hammered on all the time by all the bad guys out there on the internet. So anything in that DMZ, I need to make them hardened and only put information out there that I want the internet and the bad guys to gain access to. So I only put my public zone out there and never my boboville.lan private zone out there. That's the split DNS. There's the architecture, very typical example of the DNS architecture that supports the split DNS for internal namespace support for your Active Directory services and public namespace support for users of the internet to gain access to your public web services. We'll quit here and pick up on other networking infrastructure services in our next lesson. Let's continue with a look at the DNS client side. That's the domain name system client side. Now, the DNS client is referred to as a resolver. That's a DNS client. So when I say the term resolver, that's the user who is trying to resolve a fully qualified domain name to the IP address so that the network stack can forward the network information, whatever it is, whether it's query or file transfer, whatever, to the appropriate system. Now, in order for that to happen, we have to get this name resolution to occur. If you look at the dialog on the right-hand side, towards the lower half of that, you see use the following DNS server addresses. We have a preferred DNS server and an alternate DNS server. So this is the client configuration. Actually, the dialog is for the basic IP version 4 configuration, and a core component of that is the bottom half, the DNS server address is preferred and alternate. And typically you'll want both of those populated because if you can't get name resolution, you are probably not going to be able to authenticate if you're in an enterprise environment, a corporate environment with directory services. And if you are perhaps using this at home, if you can't get access to name resolution services, you won't be able to browse the internet. So you must have DNS access in order to accomplish either of those things, support for directory services and also for browsing anything on the internet or connecting to servers on the internet. We must have connectivity, and that's why if we can't get to the preferred server, I provide the IP address of an alternate DNS server, and I'll query him only if that first server is unresponsive. Now, we query the DNS server when we're looking for this name resolution, as I've described, and when I receive a response back from the DNS server, the client will hold that response in memory in something called the resolver cache. That's a chunk of memory that's set aside just to memorize these name to IP address mappings. And there is a time to live stamp that comes along with that record. And whatever that time to live says, that's how long I will hold this mapping in memory, and then I'll discard it when that TTL counts down to 0. Now, in Microsoft environment, the default setting is typically 60 minutes for this time to live. However, that's very adjustable, and there might be times where you want to run that number way up or run that number way down. Keeping a very short TTL means the information will remain fresh. In other words, if somebody changes an IP address, I'll query more often, and that way I'll more quickly learn of the change of the IP address. Or if the environment is very static and those IP addresses don't change very often, I might run that TTL up to, let's say, 24 hours so that I'm not polluting my network environment with unnecessary DNS queries and responses. DNS is a very light-duty protocol, so it's not too heavy. But at the same time, if my environment is very static and these mappings aren't moving around very much, then perhaps I can live with a 24-hour TTL. And when the client holds this in memory in this resolver cache, he doesn't have to submit a query because he's already got the IP address memorized for webserve1.boboville.com, for example. And so there is no need for a query because I've already got that information memorized. So this is the resolver side, the client side of DNS. Now, there are some attacks with DNS because DNS is not authenticated. In other words, the users, the resolvers, are anonymous. And as a result, this lends itself to vulnerabilities. It might be a bad guy who's trying to interrupt or interfere with this name resolution process, because if he can destroy DNS, he can disable your ability to successfully authenticate in your directory services environment, and he can destroy your ability to browse the internet completely, or using something called DNS poisoning, he will overwrite mappings, a legitimate mapping. Let's say you want to go to www.microsoft.com. He can overwrite that mapping, legitimate mapping that would actually take you to Microsoft.com servers, and he can put in his IP address that is perhaps a bogus, spoofed Microsoft.com web server, only it's going to download malware, viruses, Trojan horses, things along these lines into your computer. So this is a very desirable and fairly common attack vector for the bad guys. So how does this work? Well, one approach is that the bad guy can break into, somehow compromise a DNS server through one of many different vulnerabilities that the server may have. And not necessarily breaking into the DNS system initially, he'll attack some other vulnerability on that server and then eventually gain access to the DNS system through privilege escalation and other forms of ancillary attacks. But at some point he gets to where he can alter the mappings in the DNS system, whether it's in its cache memory or whether it's actually in the database, depending on the nature of this server. And if he can overwrite a mapping or inject a new mapping to a bogus address, he now can redirect traffic to whatever system he wants. You're going to, let's say, google.com. Well, he can put in the IP address for his spoofed server for google.com, and instead of it being a legitimate search engine, it's now a web server that is going to pump down malware onto your system. The governments around the planet have recognized that if the bad guys break into the public DNS system, they could compromise all e-commerce on the internet. And this would be devastating to the global economies, the global economy singular and the individual nations that make up that global economy. Their economies could be destroyed as well. So this is a huge vulnerability and a huge threat to global economy. So the proposed solution is called DNSSEC, DNS security. And the point here is that if a bad guy had the ability to break in and overwrite these mappings, or could perhaps send bogus responses. So you are a resolver, you send a query for www.google.com. If a bad guy could inject a malicious or unsolicited response for www.google.com, only instead of it being a legitimate mapping, he points to the IP address of his bad guy server, that would be the way he'd compromise the systems. What DNSSEC proposes is that all these DNS responses will be digitally signed, and you, the resolver, would validate the digital signature on that DNS response. So this would imply that the response came from a legitimate DNS server, not the bad guy injecting a response, and that the response hasn't been altered. That's yet another attack vector that the bad guy could implement, and he would capture, as man in the middle, he would capture the legitimate DNS response, alter the DNS response by manipulating the IP address pointing to his bad guy web server, and then forward that response on to the client. So DNSSEC would prove authentic DNS server response and that the response hasn't been tampered with or hasn't been altered. The integrity of the responses is still high. So DNSSEC is the proposed solution, security solution for some of the major attacks on DNS. It's being slowly rolled out now across the globe. There are some weaknesses in it. However, at this point in time, it's the best we have. It hopefully will improve as it gets deployed and ages. We'll take a break here and we'll pick up shortly.